Hi, good morning, everyone. Welcome to Tucson. Welcome to ESIG. Here's Leo Jiang. I'm from ESIG. Today I will be talking about a very fun topics here. When I came to Tucson, I realized two things. I think this is a really perfect place for this tutorial for two reasons. You can see that the sunshine here, the beautiful day, sunshine is strong, means it's very good for solar. The second part I realize is that Arizona and Tucson, they are booming. A lot of industries moving, population is growing. That means the load is increasing. So this is really the topic for today. How did you manage the DERs? How did you get more load into the grid to manage the congestion? And this is where we are. But before that, I do have a couple questions to my tutorial speakers here. How many of you have a rooftop solar? You have one? How about you? No? Okay. How many of you have EV chargers at home? This guy is really the perfect speaker for today. How about that audience? How many of you have rooftop solar? Only one. One? Wow. We are the renewable, like we are the power engineer, we're the renewable guys. Only one? How about EVs? How many of you have EVs? I know, I understand why you are the speaker today now. Fantastic. So how many of you look at the hosting capacity from your utility to serve your region? When you have your rooftop solar, we have EVs. What it means from the utility? Have you ever looked at the hosting capacity map? Yes, at your house? For your house?
No, my utility doesn't publish a hosting capacity.
Oh, bummer. We will talk about which utility will publish it then. All right, fantastic. So today's topic is really trying to increase the DER load, the hosting capacity with the flash interconnection, the flow controllers. So the background here is that with more of the DERs integrated to the grid and with more load growth, and our grid is very stressed. And you will see some data how stressful it is now to accommodate more DERs in the load. But before that, I want to quickly introduce our tutorial speakers here. Here's Leo Jiang from ESIG. I will kick off the introduction, but we have the So should I talk about this? Okay, great. So I have our speakers here. If you can use a microphone, that's even better. Just by the name, how about that? Mike, you want to start?
All right. So I am Michael Hannestead with RLC Engineering. We are based up in Maine, so pretty far away. And we are a power system engineering consulting firm. We help utilities, ISOs. I've been with them for about 10 years. I also do some work on DER, thank you, integration. And I'm the vice chair of 1547.7, which is the DER interconnection standard that's in revision right now.
Fantastic. Fantastic, thanks. All right, John.
All right, I'm John Groders. I'm with Internex. We're a power systems consulting firm as well, based out of Tennessee, but do work across the country, do a lot of work with helping utilities develop grid modernization roadmaps, also do a lot of modeling and simulation work, some of which we'll talk about today as a case study, what we've done with flexible interconnections.
Sit on. So I'm Mark. I also am with Internex, and I helped with some of the modeling and simulation for the flexible interconnect project that we'll present later on today.
Thanks. Last but not least, Zach.
Good morning. Zach Pollock, Director of Grid Strategy and Emerging Technology at Xcel Energy. For those that don't know Xcel, we serve 8 states sort of west of the Midwest. We've got 3.5 million electric customers, 2.5 million gas customers. Been working closely with a lot of different teams internally on flexible interconnection. More broadly, what are we doing to increase hosting capacity, both from a load perspective and also a generation perspective? So look forward to it.
Yeah, thanks so much. All right, let's look at some fun charts here. So the first one is the hey Ryan, the slide doesn't flip. What? It flips here, but no. Oh yeah, it's delayed. It seems like it's very delayed. There's a fun charts here. One is look at the U.S. solar installation, the forecast. If you are not seeing so many solar panels, but you will see it pretty soon. So this is the forecasted capacity for the solar. If you look at the trajectory at this moment, we are at a peak about the installation, annual installation now. Now, if you look at the right side as really the national summer peak load growth, but the load growth is primarily due to the electrification. But if both of the curves just tell us one message, the grid will have more DRs. We will see more load into the grid. And for a lot of the DRs and the electrification, the distribution grid will be the first line to get them integrated. So the quick question here is that, is the distribution grid ready to support the continuous DR and the load growth? If we have shortage of the capacity, what should we do? There is from the utility side, it's very delayed, Ryan. From the utility side, there are about half of the state now across the country, they publish the hosting capacity. Hosting capacity, for example, in the upstate New York or New York State, in general, there are three hosting capacity map the utility publish. One is we call the DR hosting capacity. This one I using the NICEC and RGNE, the website, just as an example to show how the hosting capacity look like. And basically for each feeder circuit, at each feeder circuit, you will see the different colors. It basically means at the different segments of the feeder circuit, what's the maximum DRs that can be integrated into the grid without adversely impacting the power quality or reliability under current configuration and without requiring any infrastructure upgrade. So the hosting capacity was really published primarily for the developers, so they can screen for where's a good spot to integrate the DRs into the grid. But I also want to give a caveat. This is not a replacement of the utility interconnection procedure. This is just give you a preliminary feeling where's the good spot for your DRs. So the developers are primarily really focused on this. There was one joke from the developers that told me one thing, is that Leo, why the utility suddenly they update their the hosting capacity, I get more good spot for my DRs. So by the way, the utility I wouldn't say constant, but they regularly update the DR hosting capacity at least yearly. So that's what the developers look at. As I said, the second hosting capacity map they publish is a little bit delayed by the load. We call it electrification hosting capacity. The concept will be very similar. Basically, without really any requirement of the upgrade, without any thermal and voltage violations for each feeder circuit at each segment, how much additional load I can host. So that is also very helpful for the developers to look at where's a good spot for my, say, if we want to build an EV charging station, where's a good spot for that? So this is as an example, how the hosting capacity for the load look like. And the third hosting capacity map I didn't talk about is called energy storage hosting capacity. If you just Google it and any utility in New York State, you will see the map there online. But that will give you the taste about if you're trying to integrate energy storage into the grid, where's a good spot for that? I know that some of are saying that their hosting capacity is not published yet, and it's a little bit delayed. I will show the picture pretty soon. This is published by the U.S. the Department of Energy. This is where the hosting capacity are published. If you look at across the country now, there are roughly about 58 utility service territory or statewide hosting capacity maps are available. So roughly half of the US states has some kinds of hosting capacity is available. If you look at that, I'm from upstate New York. We are pretty green here. It means that both the electrification and the DER hosting capacity are available. That's where the NICEC and RG&E, part of the Avangrid utility, the figures I get from. So this is the status for the hosting capacity map currently published. I know that you are from the Texas. Texas here is a little bit white. So it's your job to get it published someday. With all the hosting capacity, so the DR developers or any developers will look at the hosting capacity, trying to see where's the good spot. And I'm just using the upstate New York. When I say upstate New York, indeed, this is four utilities aggregated data. I analyze the data here. If you look at the left chart here, this is for the DR hosting capacity upstate New York. This is a probability density function. The x-axis is the hosting capacity. What is the additional available hosting capacity? The y-axis is the probability. Now, this is accumulated probability. So just trying to give you a little bit example here. When we talk about DR hosting capacity, how much additional headroom we have to support the DR growth. The data is a little bit concerning to me because 20% of the feeder circuit has zero hosting capacity currently. That's what this curve shows. The average of the hosting capacity currently, available hosting capacity for upstate New York is about the 2 megawatt MVA. That is also concerning to me because in New York State, currently, majority of the DERs, they are integrated into the upstate New York utilities. We also have our friends from ConEd and PSEG, Long Island Power Authority there, but they also integrate significant, but the majority is still in upstate New York. But if you look at this hosting capacity map, you are concerned. The question here is our energy infrastructure or distribution infrastructure ready to support the DER growth? So this is another figure I have. This is for the electrification hosting capacity. We did a similar analysis for this, trying to look at all the upstate New York utilities, trying to look at how many additional headroom or you have to support load growth. And this one making me sleep a little bit better. I think that's the reason I sleep a little bit better, because the average, the hosting capacity for electrification in upstate New York is about the 3.3 MVA. Compared to 2 MVA, it is 60% larger. That makes me happier. So basically, if we have more EVs to the grid, if we want to electrify the building sectors, the upstate New York definitely has more headroom for that. And that makes me sleep a little bit better. Next time, if I want to change my my furnace to the electrical ones, I feel like I'm not created too much trouble to make the grid stressed. So this is the hosting capacity map. Now you look at that, you see that where is a good spot for your DERs for your load. If there's no capacity available, you will need to work with the utility to upgrade the grid to accommodate your DERs and the load. Here is just a table. It's from the Avangrid. Avangrid did a flash interconnection seminar at the ESIG. This is the table is from them. This is just trying to highlight in red. This is just trying to give you a taste. When you are short of the capacity, you need to do the grid upgrade to accommodate your load or the DERs. How much money you need to pay to upgrade, we call the grid reinforcement, to get your DERs or load integrated. It's easy to get into a few $1 million. This is the table is published by Avangrid for the solar interconnection there. as an example. And this also will be changing, depends on the utility. For example, if you are going to the city, that's a different story. In general, that will be more expensive. So this is based on the urban grid in upstate New York, some of the example project, the grid reinforcement cost. So the message here is simple. If you don't have the grid capacity to accommodate your DRs or load, if you need to do the grid reinforcement per project, it will not be cheap. It will be a few hundred, it will be a few million dollars for the grid reinforcement. Then the question here, oh, we have a small slide, basically a few questions here. If you have a grid constraints, what will come into your mind? What's your what the solution you will think about for this? If you can join me for the slide, just trying to, there's only, I think 3 or 4 questions. If you can join me with that, share with your thought, that would be great. Let me see if I can scan the code as well to make sure the code is running. It's running, good? Yeah. Stay here a little bit. So the first question is, I think the first question here is, what is your background? But it doesn't load up here. Oh, you're from the utility. Wow, 100% utility. Are you sure? Right, okay, I'm waiting for that. We're trying to manage the technology here, I know, right? Yeah, okay, great. For others, or research organization, regulatory, RTO and ISO, okay, consultant, pretty diverse, which is great. More? Fantastic. Seems we have a pretty balanced audience here with a different background. All the questions you have to answer before you can do anything. And when you go to the last question, it says select bio, but you can't go and select one. Oh, really? Okay, let me see. If there's any glitches, if others share more. Okay, let me skip this one. Okay, we'll probably pass that one. This is just trying to give you trying to know who is here better. So it seems that we have a pretty diverse audience here, which is great. You all have a different perspective. And then the second question here is, what's your concern about lack of a hosting capacity? So like whatever is applied. Your little girl seems that is more concerning. Interconnection costs, uncertain time, operational risk, miss the goal of the DRs. Great. Fantastic. Seems the load is a bit concerning to us. Okay. Customer experience, yes. Right? Our job from the utility side is really trying to serve the customers. At the end, all the power industry and energy infrastructure is trying to support the customers, right? Definitely, we agree with you. The customer experience is very important. How about this one? What are the potential capacity solutions? Proactive grid upgrade. That's a fantastic answer. We also have different opinions here. Load flexibility, yes. And indeed, it's a hot topic as well. And flash interconnection, energy storage, flow control technology, Great, fantastic. All of the above. Oh, that's even better. Correct. Fantastic. Oh, thank you so much for your input. So basically, with all the DR and the load growth, I called it this one. You have the short-term or mid-term capacity solution. That could be the flow control technology that we will be talking about today in this tutorial. That will be low-cost solution technology. Indeed, our speaker, Mike Hannestad, he involved in two pilot study. One is at the national grid, the other is Georgia Power. I believe the field demonstration demonstrate the technology can increase your DR or even the load hosting capacity by roughly maybe 10 to 20% with a fairly low cost. And indeed, the utility even told me that from the utility engineer, they shared with me saying that, Leo, we are trying to scale up this technology deployment in the utility territory. The second technology is a flat solar interconnection. The Avangrid did this pilot since 2020. If you want to know more, the ESIG has a webinar from last October. It's online as well. So that pilot study that really increased the DR hosting capacity from 7.6 megawatt to 15 megawatt, which is significantly increased with moderate curtailment. And if you want to know more, the tutorial will, the webinars from last October will give you more details. And if you want to look at a long-term solution, that will be the proactive planning as someone selected, or integrated planning. Indeed, the DR working group in the afternoon, and also the workshop panels on Tuesday and the Wednesday and the Thursday will shed more lights on this topic. We do have fantastic panels on both of the topics here. With that, I will transition to Internex and Excel to talk more about the flash interconnection with the overviews and the case studies at the Excel Energy. John, pass on to you.
All right, thank you. Getting us kicked off, Leo. So yeah, we're breaking this tutorial into two parts. So this morning we're going to be talking about flexible interconnections and get into some real case study on that, and then we'll break and then come back, and Michael talk about the load control. Clearly, he's doing it by himself. I had to bring two experts in with me to cover my portion, so he wins that one. So on the flexible interconnection, so we're gonna kind of break it into three parts. So I'm gonna give you just kind of an overview. I know flexible interconnection can mean a lot of different things to different people, so I'll try to kind of set the stage as far as when we're talking about it, what we're getting at, and then Zach's here from Excel, and he's going to give you just a little bit of background of why Excel is looking at it, kind of, you know, their journey into flexible interconnections and kind of where they're going with that. And then finally, my colleague Mark is going to talk about a case study working with distribution modeling and how to model it to get to look at a particular flexible interconnection example. So with that, I'll do the overview. I kind of briefly touched on who Internex is, but basically we've got, you know, about 4 key service offerings, everything from kind of grid modernization, guidance and oversight, and then also we get into a lot of modeling and simulation work, which comes into play here when Mark talks about that part. So I did want to first just kind of mention a key report in the industry. It's a little bit older now, but this was kind of the beginning stages of when flexible interconnection really started to come into the industry, and EPRI put this together. And it's anytime you see a industry presentation on flexible interconnection, inevitably you're going to see graphics directly from this report. So including this one this morning. So I wanted to at least kind of point it out. Probably probably a case for an updated, some more updated content, but it really did kind of hit on this up from an early standpoint. Okay, so just talking about flexible interconnection. Oh, sorry, we're trying to. There we go. Thank you, sir. All right, so just to get it kicked off. So really what we're talking about is trying to enable more DERs to interconnect beyond just traditional firm hosting. And we're going to talk about different ways that this can be done, but basically either through curtailment, whether that's scheduled or more of a real-time dynamic. We'll talk about those different methods and kind of what goes into it. But how can we get more DERs connected with the grid we have? So we want to increase grid utilization, but obviously maintaining safety, reliability. That's obviously paramount. So this definitely requires some updated planning practices that we'll discuss. And it may also require some increased communications networks. It also may, depending on how you're doing your flexible interconnections, it may require more advanced control systems and interaction with the DERs, all of which we'll touch on. And that graphic just kind of gives you just a quick, we'll talk about this in a little bit more depth, but basically your conventional interconnection is going to always look at the most conservative approach, looking at the absolute worst case scenario, and then making sure that if it's full nameplate capacity, that those will never those will never create a reliability or violate any sort of thresholds. What it does mean, though, is that means you're leaving a lot of capacity on the table that you could be leveraging those DERs during times that the grid would actually allow it. So we'll get into how that can work. Now it's not. Oh, over, not down. Okay. All right, so just briefly, why flexible interconnection is emerging now. I mean, there's a handful of things, but mainly it's kind of a lot of what Leo was talking about. There's continued DER growth. It's pushing distribution systems towards those hosting capacity limits. Conventional interconnection methodologies kind of collides with this, and it's like, how can we look at some other ways to do it? And obviously, affordability is a huge aspect in everybody's in every utility right now. So, and infrastructure upgrades are costly. So what can we do in the near or midterm to potentially offset it? And really that flexible interconnections kind of offers that bridge, or could be a more long-term solution, but really it is kind of, as Leo talked about, it's really that near midterm solution to try to open up capacity. All right, so Leo talked a lot on hosting capacity. I kept this slide in here just to keep it complete, but really what I could have said is what Leo said, because he did a great job of talking about hosting capacity. A key thing about this, so think about hosting capacity is definitely very time dependent. So you need to look at what your constraints might be. So in this case, looking at a thermal constraint, looking at a voltage constraint over a period of time, you want to make sure that hosting capacity is always taking into account whatever that most conservative hosting capacity, or sorry, that limit to create the entire hosting capacity. So traditionally, what you would do is then take that DER capacity nameplate and make sure that at that single point of interconnection that you will never violate any of that hosting. So typical interconnection process. So really you can think of this as there's typically three outcomes that can come from an interconnection process, like for a DER interconnection. One, you can connect to the existing network, no modification needed, there's no concerns. Two, okay, the DER can connect, but you're not going to be able to connect at the full capacity that you want. Or three, okay, if you want to connect at that full capacity, then we have to, it'll trigger a system upgrade before you can actually connect at that listed. Really what flexible interconnection is designed to do is create a fourth option where, okay, we've run some analysis, which Mark will touch on. we see that there are certain periods or certain situations where, yes, you will violate it, but other times you can be you can be at full nameplate capacity. So that's really kind of the whole crux of flexible interconnection, allowing more and allow for that flexibility in that connection process. So what are some common issues that are triggered when you are doing like an impact analysis? So we'll first look at the two on the left, because those are the ones that can directly be modified or addressed with flexible interconnection. So one might be a thermal overload. So typically either you're hitting a limit on maybe a conductor or a transformer, and you have to just keep that into account. So conventional utility resolution obviously would be the replacement or installation of a transformer, or maybe reconductoring to allow for that full nameplate capacity to connect. Voltage regulation is another big one. When a DER is generating at full nameplate, it may cause excessive tap movement, or it even may violate some limits of that feeder on the voltage side. So again, the traditional resolution would be installation of devices, whether it's capacitors, changing of tap positions, or maybe some voltage regulators to adjust or just simply not allow that device to connect. So those two are directly can be addressed with flexible interconnection, but two other ones just to kind of complete the story. So there could be some power quality issues with connecting. So obviously, then that would trigger a lot of times a installation of some PQ remediation devices at the customer site, or again might require some upgrading of some conductors. And then obviously protection, and a lot of that comes down to anti-islanding. So what needs to happen there? Maybe it's a direct transfer trip situation, or making sure that there is some anti-islanding protection involved. So we're not going to touch on those two on the right, but the two on the left certainly come into play when it comes to flexible interconnections. Okay, so it took this long to get to, okay, what are we talking about when we talk about flexible interconnection? So really it's a DER control strategy used to defer or avoid system upgrades or increase distribution system utilization. So again, looking at the one on the left, you take your worst case hosting capacity, your conventional limit, and then you're going to make sure that nameplate capacity never violates it. Whereas again, what you're trying to do, and this is kind of like aspirational, but basically allow for more of it, and then just making sure that you're curtailing or making sure that they're not generating at full capacity at times that it would be violating those limits. So here's a key distinction that I think sometimes we gloss over when we're talking about flexible interconnection. So static versus dynamic. So static meaning, and this is going to touch on a lot of what Mark is going to talk about on his case study, but you run your system analysis, you run all your modeling and simulation, and then the utility then at that point provides a set schedule. They know, okay, these are the times, days when curtailment is needed, and it's very specific to those to that schedule. And then the customer will then be responsible for staying within those limits of the schedule. And I wanted to put that last one. So the utility may or may not have that real-time knowledge, whether they're adhering to it, depending on, what that connection agreement looks like. But that's good to understand that that's kind of the static side. Now, more dynamic, more closer to a real time. This would be where, there still probably was an upfront study. They know how much curtailment may need, but they're not going to set a set schedule. Instead, they're going to provide a forecast, often maybe day ahead. It could be more real time than that, but basically the customer then is responsible for acting a little bit more, little more quickly. This may also even get into actual real-time monitoring and real-time control of those DER sites. So it gets, I would say the static one, obviously less complex, easier to implement. Dynamic, you're going to have less curtailment because static will not obviously lead to additional curtailment. It's a more conservative approach, whereas dynamic, you will be able to allow the DER to produce more, but again, it creates more complexity and potentially more advanced systems need to be looked into. So then taking that and looking at some control schemes. So first one is what we're calling a fixed constraint. So this is for the static interconnection type. Again, it's time-based or scheduled. And basically the utility or interconnection entity, says these are the fixed schedule and constraints that you have to operate within. Again, pretty simplistic, pretty straightforward. The downside is you probably are going to have over curtailment than what you need. Then kind of getting a little bit more complex, but still, not fully the most complex system. So a localized constraint. So this could be used for either static or dynamic, but it really is localized control, and that monitoring point is local at that point of interconnection. So whether that's a fixed schedule that it has to stay between, or if there are actual fixed limits at that local point of interconnection, that then that customer is required to stay within and manage within that. And then kind of going down that scale of complexity, some multiple system constraints. So this would be for a more dynamic interconnection type, but this is where you may have a centralized control system with local coordination, but the monitoring points might be multiple points in the system. You may, when you're doing your system analysis, you know that these are your key constraint points on the system, and you actually want to have some monitoring of those points and be able to react pretty much in real time to those. So again, introduces a lot more complexity, but again, it allows for a lot more DER output. This is just a screenshot from one technology vendor that does more of that real time flexible interconnection where it is looking at multiple monitoring points. So what we're seeing here is there are a few different thresholds that basically would trigger a reaction. So the green is just a load, the loading of the DER, and then when it breaches some of these thresholds, then it wants to react. So what we're seeing here is, perhaps what probably happened here is a large load maybe came offline, and now there's overproduction and a curtailment is needed of this DER generation device. Yeah. I didn't quite hear. This is
DER point in the feeder.
It's a point of interconnection at the feeder. Yeah.
If you can use the speaker, that would be better because it's recorded. If you don't use the mic,
yeah.
We
so
capture your
okay,
voice.
okay, yeah. So this, it probably was. I don't know this specific case, but I'm pretty sure that this would be a point on the feeder that it's monitoring, and it's basically it's determined that this is a constraint point that they want to look at. So yes, again, something that might trigger this was a large load come off, and now you've got overgeneration and you need to react. Does that make sense?
Yeah, I guess the question is, so if that's what happened, if you're monitoring some point in the feeder where that constraint is happening, is the logic all behind in the controller of which units to actually change?
Yes, exactly. So all these points and the determination of that threshold is all done prior to. That's exactly right. You want to,
So that would mean that if I put a new DER on this feeder, I have to completely redo that logic?
Potentially. Yeah. So again, you're right. So it adds additional complexity. But yes, as the feeder network changes, you may have to go back and look, okay, are these constraint points, are these thresholds still what we want to use? So sure.
Oh. Do you have to say our name or no?
What's that?
Do we have to say our name or not? Can we just say the
Oh,
question?
sure.
Okay. Hi, Nancy Morales, Bonneville Power Administration. So I have a very simple question. When we're talking about DERs, is that dispatchable? So like a battery, or are we talking distribution energy resources? Sorry, I've been lost. So what
Okay,
is
so
DER in this instance?
right now we're talking about DER and mainly generation. We're going to also talk about like this as a load curtailment, but this is mainly probably a PV distribution and being able to curtail. So yes, battery storage could come into play if that's also as a way of curtailing, certainly. So battery storage, absolutely. But if there's no battery storage, then this is just purely trying to curtail when there's certain limits that are being breached.
Okay, thank you so much.
Yep. Sure. I don't know. Yeah.
Okay, so I have a couple of questions. I'll try to
Okay.
articulate my brain. What I'm seeing so what we are trying to do here with all this flow control and et cetera is essentially you have a capacity limit on the feeder circuits. And then for you to get the resources into the system, you're doing all these kind of things so that your resource that is connecting to the system doesn't overshoot or undershoot the available feeder capacity and circuits. I get that, right? My question is, it's a given that your feeder capacity is limited, like Leo showed in his earlier slide. It's also a given that your load is going to keep overshooting your installed circuit capacity, transmission feeder capacity, right? So my question, if all of what I've said is correct, my question is, all of these control and the logic systems that you're putting in is transient, trying to optimize, bring these distributed resources into the grid and kind of fill in the gaps as to where the capacity gaps are. It's temporary. So the question then is, you have to increase the capacity. So everything today is transitional. Do you have a timeline as to the capacity has got to increase? What's the slow moving graph of when the circuit capacity increases? And all of these, are they going to move? I mean, all of it, this is dynamic. I mean, so what you're saying, like the question is asked, if things change, you got to change things. So there are two things here. One is, what is the timeline of capacity increase itself? What's that trajectory? Years, months, weeks? And the next is, how is whatever you're talking here going to respond to that larger envelope change? Those are my two questions, if I make sense.
Yeah. I mean, I think you could probably have an entire tutorial on what needs to change for distribution planning and how much quicker it needs to be in reaction. Absolutely. Yeah. So I don't think anybody could say, what is that timeline? I know I saw Zach nodding. I think Zach will probably touch on, he's definitely can come with the perspective of like Excel's distribution planning and how that's changing to adapt to things like this. Cause you're right. It has to become okay.
He asked, if things change, which means that I don't know the name of the person who asked it. If things change, that is, if the capacity changes, feeder circuits change, whatever, then everything that's shown here needs to change. So the question is, I'm a software guy. So how difficult is it to change? My car gets updated on Wi-Fi today. So couldn't all this thing get just updated? These are controls, flow controls. So you could simply re-gig all of the control. Is that possible? That's the question.
So maybe I'll take your analogy. If you think of this as a device, this is maybe kind of like a firmware where it can do, small tweaks right now. But you're right. The biggest thing is we also have to look long term, and there's a bunch of systems. So, I mean, I think you kind of have to do two things at once. This can be kind of a band-aid, kind of that short, near term to get more out of the system you have. But at the same point, you are also thinking long term. Well, now you're getting to specific. So it depends on what you're talking about as far as like a device or as far as, because again, to do something like this, it does require more advanced control systems. Absolutely. Yeah. So something like this, you would have to have a lot. Your whether it's through an ADMS, whether it's through like a standalone DERMS, whether certainly it would require open more. No, good discussion. Okay, so I'll just kind of get through the last couple of slides here, and then jump into Zach's part. So obviously there's benefit from both the utility side as well as the developer side, but really what we're talking about is in a, when you're just doing a standard, interconnection, there comes a point where that interconnection is going to be limited on capacity. So beyond that is really, this is where that flexible interconnection comes into play. So, option 3 might be overly curtailed. This might be considered like the static or timed varied, where you can't connect or you can't over generate. It allows that more operation in there or more capacity, but it's still reduced. And then you may have like what we're showing here, like option 4, where it's increased utilization, but again, it probably comes at more complexity, like we were talking about, some sort of advanced system, a DERM system, or some sort of control system that allows for that. So from the utility perspective, it hopefully allows maybe delays some system upgrades while, you can get those planned out. But from a developer perspective, I mean, this allows them to at least connect at a higher capacity than maybe traditionally the hosting capacity would allow for. So, but for them, obviously, then that might be increased revenue, but they have to do it on their end to see, what does it make sense. And almost any time that we talk about flexible interconnections, part of the process will be telling the developer, here's what you can expect. I mean, a developer's not going to go into an agreement like this and then just not know how often it's going to, how often the curtailment. I'm sure that will always be in that contractual agreement as far as what that and amount of that curtailment might be. Okay, so up until now, we've been talking about mainly just focused on DER generation, but I did want to at least touch on flexible interconnections for loads. So this can go in the reverse direction as well, where a large load may want to come on. And again, we're typically talking about distribution network, but they may want to come on, and same thing, there might not be capacity for them. So in a reverse direction, large loads could also be thought of as flexible interconnections. So basically, customers, again, you do a system analysis, and then based on that, the customer may have to agree to operate within those defined capacity limits that may vary by season, time of day, real-time grid conditions. Again, this can be either time-based or it could be more real-time depending on what you have in place. And then just kind of this last one. So we're seeing these increasing on the distribution network, and it's mainly some large loads. Now, data centers, I'll put with a big asterisk. A lot of data centers are not going to, well, no data center wants to be considered a flexible load, but if you want to get more onto the system, both distribution system and transmission, there's going to have to be some look at, that flexibility. And there's a lot of industry groups that are looking at data centers for flexibility, but it's not trivial. But more things that do, like EV charging hubs. Excel's actually looking at an EV charging location that could be flexed and curtailed during certain grid constraints. Maybe hydrogen production, and then like as we see more building electrification, part of that might be using some of that increased loading as a flexibility. So just wanted to put that caveat there that this can also be used for loads. So challenges, I'll just briefly go through. I mean, obviously there's several things. So if you do want to do more of a real time or controlled, what are your control systems in place? Do you need to upgrade them? What type of control? With that, do you need to upgrade your communication networks, or especially if you're really relying on these to be an asset for your reliability? What does that look like? And then anytime more controls, You need to make sure cybersecurity that you're taking into account, and then performance. Can the utilities, when they're, I mean, a big pushback of a lot of this is, can the utilities rely on this to actually, can they take that reliability and build it into their planning? Curtailment analysis, again, oftentimes when you go into this, you're going to it's going to trigger a study, a system impact look to make sure what that curtailment might look like. And then what is the contractual rate structures? What does that contract look like for flexible interconnection? So just all things that need to be taken into consideration. And I'll just quickly touch on, where is this already being utilized? So I highlight the UK. This has been pretty standard in the UK for a number of years. This is a direct poll from National Grid in the UK, where they actually offer different flexible connection options. So just the ones we talked about, they offer a timed connection. So that's going to be more curtailment, but it's cheaper for them. The analysis is quicker, and they can they can get through that process quicker. They also have like an export limitation scheme, so that's more of your kind of localized control if you're hitting certain limits at times. And then the most complex and will be the most costly, but will also it will reduce the amount of curtailment, is what they call load managed connections. So this is using kind of that real-time SCADA data and their system they have in place to actually monitor it. So even though it's somewhat new and up and coming in the US, there are places that are using it pretty prevalently, and like in the US specifically, some areas that are really starting to see more of it. And Leo certainly can talk later about what Avangrid's doing. They've had a pretty successful deployment of some flexible interconnections. National Grid as well in the Northeast. California just approved a request back in 2024 from the PUC. Basically, what they're calling it is limited generation profiles. I mean, that's basically the same thing as a form of flexible interconnection. Colorado, which Zach will touch on, but there's been legislation that has helped kind of push some of this, and Xcel Energy is now starting to offer flexible interconnection to some developers. And Illinois is another one that has highlighted it, and I know I'm missing some, but these are some of the areas we're starting to see more of this start to take shape. So with that, I think I'll pass it on to Zach, and he can kind of talk about the utility side of it and kind of some of the motivations for it.
Thanks, John. Anybody need a quick stretch break? We've been going for an hour. Yeah, take a minute. All right, we'll try to get going here again. Everyone properly caffeinated or stretched? Good morning, Zach Pollock, Director of Grid Strategy and Emerging Technology at Excel Energy again. I'll talk a little bit higher level and sort of zoom out a little bit from some of the technical details. I'm not an engineer, but I think I've got 4 engineers up here. So if you have any really technical questions, I'm going to punt to them. It was touched upon a little bit, but there are a lot of interrelated concepts to flexible interconnection that I think are important to highlight in relationship to what's going on in the utility industry. So Excel, much like a lot of other utilities out there, we operate in 8 states. We have a $45 billion capital plan as of a year ago. That increased to $60 billion for our next 5-year planning cycle. So what used to be a pretty sleepy, boring industry is getting a lot more exciting with the load growth that we're seeing on our system. We're seeing increasing DER penetration that Leo talked to earlier. And all this ties back to flexible interconnection as a tool to potentially help us out with broader meta solutions and opportunities with preserving affordability, better utilizing the system, et cetera. So I'll talk through each of the key aspects of the slide here and how that relates to what we're trying to do strategically as a utility company. So if you look at the first box about making DERs an asset of the system, you think about where we've come from as an industry. You know, the first generation of solar and DER was really about direct customer benefits. And if you look at states like California with net metering 1.0 and how that's evolved, there gets to be a point where direct customer benefits don't really provide a benefit to the overall system, the other customers that are overall users of the grid and how that grid is paid for. So we're trying to find ways that we can position DERs actually as an asset to the system. Some of that comes with things like locational value and being able to do things like flexible interconnection. The reason I say that is because we're starting to see trade organizations, solar industry start to position and advocate for socializing the cost of interconnection upgrades. Historically, from a policy perspective, those costs have been directly paid for by developers. But as we start to see more of that push to socialize those costs, if developers are facing large upgrade costs, they can socialize those through the customer base. That becomes a problem and a challenge for our customers because it's going to put upward pressure on their costs. So we're looking at opportunities like flexible interconnection, as John pointed to earlier, to be able to better insulate or reduce some of those costs. On the load side, there's this question of system utilization. The more kilowatt hours that we can put through our system in hours that previously didn't have load there, that can help put downward pressure on rates, which also improves affordability. So as we think about the next sort of phase of leading the clean energy transition as a utility, position DERs to an asset to be an asset to our system. The next one is a bit more operational. So as we start to see higher penetrations, we're seeing many things that John mentioned earlier, voltage rise on circuits with heavy solar penetration, in areas where we've got heavy clustering of projects like community solar, which is front of the meter generation. We're starting to see some backfeed on transmission. So we're also looking at flexible interconnection, more real-time and dynamic control and operations as a means of mitigating some of the operational impacts that we're starting to see in the system today. The third category here is really getting back to the customer experience that was mentioned in the survey question. So we're looking at opportunities as the system is growing a lot more dynamically to provide bridge solutions for our customers, both on the generation and the load side. What's unique about today and the world we're operating in, we'll talk about this tomorrow in a proactive planning panel, but load is changing in a way that we haven't seen in the past. So, you think about how load forecasting was done historically. It was based upon class averages. So we assumed that every customer behaved sort of the same way, and we didn't need the granular level of detail to be able to figure out where that load is going to materialize, at what point in time it is. That doesn't work today. So we're starting to see clustering of massive amounts of load growth from a residential perspective. Think about examples we've seen where, a customer may put in some rooftop solar, and then they go get an EV, and then they go get a heat pump, and it's got electric resistance backup heating. So you're talking about going from what may be 6 or 7 kW of demand on a residential household to tripling in the span of a couple of months. So we're looking at opportunities to implement flexible interconnection in a way that can meet the dynamic nature of the grid today. Simply building infrastructure is not going to be a solution that's going to be able to do that in its entirety. So we're looking at solutions like flexible interconnection that can help meet 20 or 30% of the need. To be clear, and it was mentioned earlier, flexibility is not going to obviate the need to build additional infrastructure, but it needs to be considered as part of the solution set, as part of that broader portfolio. And the last two, I touched on this a little bit, but reducing overall system costs. So if you think about the way distribution has been planned and operated historically, we're very good at putting steel and copper in the ground, and then we sort of walk away from it, and there's not a lot of real-time visibility and control of that. We're starting to get more visibility. Excel is nearly complete with its AMI deployment, so we've been using that type of granular data to better understand and unlock where we may have potential to implement solutions like flexible interconnection. John mentioned earlier, but one of the keys to being successful in flexible interconnection is moving from that deterministic worst case scenario snapshot and time analysis to doing more of an 8760 or hourly analysis that will allow you to understand what's the potential for curtailment over the course of a year, over the course of 5 years, et cetera. And that helps developers and load connections understand with some more level of certainty what the economic trade-off is for avoiding or deferring a capital upgrade that they may be responsible for paying for versus taking some ongoing curtailment. And to be clear, in the levels we've seen in the US, that curtailment percentage has been pretty low. So it's a pretty good deal for developers and customers. And then I talked about this a little bit, but again, reducing the risk of cost shift from DER upgrades. There's a lot of capital needs in the industry. So to the extent that we can take that burden off our customers and find operational and technical solutions that can help do that, we're very interested in doing that as an industry. So feel free to jump in with questions too. I've only got 2 slides here, so get through this pretty quickly. So where are we in our journey? A lot of the conversation today has focused on the technology side of this. I think, and having worked at a technology vendor for a couple of years, the technology is here, but really it's from a regulatory process, from a change management process inside the utility, inside the control room, inside DER interconnection studies. That's where some of the challenges are being met today. But fortunately, we've been pretty successful in initiatives. We've got a couple of different things going on in the states that we operate in. So I'll talk mostly about Colorado today. Just a little bit of background. In Colorado, we've got about 1 gigawatt of solar on a 7 gigawatt peaking system. Most of that is rooftop solar. We still have full retail net metering policy in Colorado. As much as we'd like to move to something more beneficial from a system perspective, we still have it. We've got a couple hundred megawatts of community solar. So those are typically 1 to 5 megawatt front of the meter systems that directly connect to the distribution system. They're not paired with load. But that's where we're seeing a lot of the challenges today. In Minnesota, also a pretty strong solar population, solar development up there. That's almost the inverse of Colorado. We've got about 1 gigawatt of community solar and a lot less rooftop solar for obvious reasons if you've ever spent time in Minnesota in the winter. So we're thinking about how we can better position flexible interconnection as solutions, some of the ongoing development that we see in both these states. In Colorado, we actually have legislation that was passed in 2024 that required us to offer a flexible interconnection tariff. That was the latest development, but we've actually been working on flexible interconnection pilots with a few developers, as well as doing some internal testing from the technology side. So we ran a solicitation several years ago that's really culminated in some work over the last year or two in Colorado, working specifically with a developer of community solar. That's where we're seeing most of the issues on our system. And the reason that that's happening is there's no co-location requirements in Colorado. So effectively, you can go build as a developer wherever you can get cheap land. So we see a lot of clustering of interconnections on the same substations in the same areas where land is cheap. That's obviously creating issues from an upgrade perspective and technical issues from voltage and thermal perspective. So really, this pilot was designed to work with the developer around some of those issues on one specific substation. We started this process with them, sort of working across both sides and trying to understand from a modeling perspective, what is the actual potential for curtailment if we were to downsize the system, or if we were to operate more in a flexible scheme with real-time or scheduled curtailment. So that's largely what happened through 2024 and 2025. And then in August of 2025, we partnered with Interconnections to be able to perform the studies and develop the overall flexible interconnection study methodology. All of that led to basically terms and conditions being developed and signed with the developer to help them understand from their perspective what the financial risk is from a development perspective. That's honestly, one of the things that doesn't get talked about often with flexible interconnection. One of the challenges is educating customers. So if you think about how most developers have operated in the US, they're used to being able to get interconnected at whatever their nameplate capacity is. They produce passively, and it is what it is. They're just used to being able to generate at their full capacity when the sun is shining. Juxtapose that to how the bulk system operates. You've got incredibly sophisticated modeling going on in the transmission system. IPPs are very good at modeling transmission risk and basis risk. So there's a little bit of a learning curve that we found on the distribution system to be able to actually understand and communicate to developers what their curtailment risk may be. That's just something new that we're going to have to educate the industry on collectively. So that took care of the study process. We've signed that interconnection agreement with the developer. We're also now in the process for some of our larger sites, both for Excel-owned sites as well as with this developer, rolling out our DERM strategy and DERMS implementation, be able to offer that real-time and scheduled curtailment. So the technology piece is well underway. I think it's also important to call out, John touched upon this in his earlier slides. There's multiple levels of technology that are applicable to flexible interconnection. For the larger sites, so we're talking 1 megawatt and above, we're looking at more centralized control through a gateway device, through a dedicated DERM system. We're also on the load side, we're looking at leveraging the capability of our smart meters for residential applications to be able to do sort of premise level load management that can offer some of that flexibility. And then on the demand response side, we have a separate what we call aggregator or edge DERM system that gives us some of that flexibility as well, but it doesn't necessarily have the real-time control that we're implementing with our what we call our grid DERM solution to enable some of those larger scale flexible interconnections. So there's really a whole ecosystem of technology solutions that can fit into that broader ecosystem of flexibility and enabling some of those flexible interconnection schemes. So the last part, we're at the point of doing a demo on dynamic control. We're in the beginning stages of doing site acceptance testing on some of the technology, but really have built a strong foundation for being able to move forward with this. I think the thing that's interesting is, again, going back to the regulatory perspective, if you look to the UK, and John and I both happen to have a shared work history of working for a technology vendor that's enabled several hundreds of megawatts of flexibility over there. It's challenging in the US right now from a regulatory perspective because a lot of these projects have been treated as pilots. There's not consistent funding streams. Developers are not sure if they're going to have the ability to do this as more than just a one-off. And that's one area where the UK has been markedly different. There's been continued funding and push for innovation to enable this type of flexibility, which in my opinion has really led to a more material liquid market for flexibility services, both on the load and generation side. So just something to think about. It's not just a technology issue. I think that part has largely been solved, but we need the right change management, the right organizational structures inside utilities, and the right regulatory structure that can help enable that. So I think that's my last slide. Yeah.
Hi. So going back to your previous slide, so going on about you signed the first flexible interconnection contract with this developer. Was part of the contract like giving them a discount for them signing the contract for flexible interconnection?
Yeah, so that's a good question. The premise or hypothesis rather, that we're testing is that traditionally in these constrained areas, the developer would be facing either a long time to interconnect or potentially significant capital costs for an upgrade that they'd be paying to basically enable the interconnection, or sometimes both. So the sort of economic hypothesis is that by offering them curtailment over the life of the project, they can avoid that upfront capital cost and potentially start generating faster. So in this developer's case, they found out that the math worked out for them. There's obviously a little bit of uncertainty and still kind of a debated topic in the industry around levels of curtailment. So, as you add more systems and more flexible interconnection arrangements, depending on principles of access, whether you do a last in, first off, or sort of pro rata curtailment, that may all change over time. But this developer at the curtailment levels that we studied felt confident enough to be able to move forward without, missing their hurdle rate for their project.
Okay, and is this developer the same developer that's doing the dynamic control, or can you
Yep.
say that, or maybe you can't?
Same developer.
Okay,
Yeah.
cool. Thank you.
Zach, thanks for the presentation. Yeah, curious about whether there's an intention to eventually upgrade the system in these cases, or is there an expectation that these types of agreements might last for the life of the system? Does that vary by technology or sort of level of curtailment?
Yeah, that's a great question. We're still internally trying to figure that out. I mentioned earlier we have to develop a flexible interconnection tariff in Colorado, and I think that's probably going to be one of the first instances where we formalize some of those decisions on whether this is more of a bridge solution or whether they'd be like a 20-year, almost like PPA. And then it obviously gets a lot more complicated when you start to add multiple systems to the same substation or feeder.
Thanks. And yeah, also curious, you mentioned kind of the residential loads that you're challenged by. Are you guys getting into operating agreements for residential devices? We just encountered our first example of that with a storage system that we had to put some kind of rules around about how that would work, but don't have DERMS connectivity to really see and enforce that.
Yeah, not yet. I mean, I think just from my perspective, having been on the DERMS side for a while, I don't think we're ever going to move to an environment where DERMS is providing controlled residential systems. I think if you look at some of the sort of smart export pilots they've done in Australia, that type of control makes a lot more sense. We're not there yet, but we're getting pushed to implement something like a limited generation profile like California's implemented.
Thanks.
Yep.
Sorry, again, a couple of questions.
Do you mind just speaking a little bit closer to the mic?
Sorry. When you say community solar, the question then is, yes, assume everything is deployed. Would the community solar be factored into the economic dispatch and unit commits, just like a nameplate generator?
Yeah, it's a good question. So again, today, most of the DER in the states we operate passively. So there's no active dispatch or no active curtailment. I would even go so far to say that it's not considered as part of the overall wholesale sort of commitments in the markets we operate in. They should show.
Sorry, then it's a big issue in capacity planning markets, right?
100%. And that, I mean,
how?
Sorry, good.
No, I'm sorry, I'm done. I mean,
yeah,
that's
I mean,
a
that
huge
goes back to the sort of broader policy environment. As we start to think about DER policy that's good for the grid and good for all of our customers that depend and pay for the grid, we have to have policies that are putting DERs in places and can generate energy in a way that actually provides capacity value. Getting more solar in the middle of the day is not incredibly helpful for us. So
thank you. One last question aside from what I asked. When you say rooftop solar, home solar, can I think of rooftop solar, residential rooftop solar, as behind the meter generation? I come from a large load perspective, and my question is based off, would rooftop solar be considered as BTM?
would it be considered what?
Would it be considered as behind the meter generation?
Generally, yeah. We consider rooftop solar to be anything that's paired with load, so behind a retail meter usually.
Okay. Thank you.
Due to the timing, maybe we will save the question at the end if we have time there. But there's good things here. I know Zach will be here for a few days, so definitely talk with him. The second one is we are pretty sure the ESIG should get Zach back to talk about the field demonstration with the DER, the terms, the dynamic control, and then with the Exxon, then right, Zach?
Either that or I'll volunteer somebody else. Yeah.
Oh, okay. Either way, well, we will have more. So basically, with all your strong interest here, this is my promise here. ESIG will invite Exxon Energy back and try to close the loop here. We're gonna see how the closed loop works for the flash interconnection at Exxon. So with that, and then we will transition to Mark. And just trying to reminder here, our break will start at 10. We will walk through Mark will walk through the case study with Exxon Energy for flash interconnection. This is more from the planning perspective, and then Zach will come back later on to talk about the real-time control as its implementation. So that the case study will be more from the planning study, and then if we have time, we will have more questions there. Hey, Mark, thanks.
All right. So like Leo said, it's more from the planning side and the modeling side, and basically just want to talk about some of the challenges we faced, how we overcame them, and maybe see some of the results of kind of that'll tie back into some of the slides that John shared earlier. So yeah, just talk about some of the objectives of the study, some of the details and assumptions that we had made, some of the thermal and voltage violation analysis that we went through, and then we'll show some of the curtailment strategies that we applied, and then talk about some of the conclusions. So pretty straightforward. So some of the objectives that Excel was looking to solve was to evaluate flexible interconnect on a certain circuit feeder that so the substation wouldn't have any issues. So the intent was to eliminate primarily some of the voltage and thermal violations that would maybe be introduced through the flexible interconnect plant, and it was a PV plant. And we do that by modifying some of the DER output. So the initial focus was on curtailment, and then we kind of moved beyond some of the worst case studies. So just static worst case scenarios, and we looked at an 8760 study. So hour by hour, how does previous hour affect the next hour versus the current hour, and so on. And then how can FI evolve over time to include some of the controllable FI, so control methods, and like John was mentioning earlier, flexible load to be included into the circuits. So the main violations that we looked at were voltage, min max, and thermal violations along the feeder. And so the following slides, again, are just to present some of the analysis that we performed using data from 2024 from the AMI program that Zach was talking about. And yeah, there's an 8760 study, but 2024 is a leap year, so 8784. It's a 5 megawatt PV plant in Colorado. So some of the assumptions that we had to make, we knew that there's some larger existing PVs here. Let me go back up. We had to model the substation transformer. Again, some of the feeder. So there's other feeders along that are connected to the same substation. So we looked at those as kind of aggregate loads, as well as aggregate all the PVs. So all the other feeders on this bus were kind of modeled together. And then the feeder that had the FI PV here, we kind of looked at separately. So yeah, some of the challenges, there was, kind of some large existing PVs, and as well as there's some future PVs that weren't subject to the FI curtailment. So we had to kind of take a look at those and how they affected the study. And by the way, we use SIME for all of our simulations and all that. So we had to create hourly profiles for customer loads if we didn't have them, and as well as other feeders on the same bus, and then all the hourly profiles for PV that exists, future committed PV, and also the FI PV under study. So I'm going to talk about some of the load allocation that we did. So these are some potential quality checks. We kind of thought about what we might have to do. We didn't have to do all of these, thankfully. But one of the main things was that we had the measurement of the substation, but we didn't have it with some of the future PVs installed. So we had to kind of take those into account and calculate what the true load would be if we didn't, if those were existing on the circuit. And then, fill in any data gaps, missing values happen. So filling any gaps with closest capacity values, filling in missing gaps and replacing overpresumption. Some loads sometimes consume more than they should, which, is erroneous data most of the time. So just making sure we clear those out of the data, just cleaning. A lot of these are data cleaning steps. And then the last step is load allocation. The load allocation method we did, SIME offers one, but we also have our own, which there's not too many different ways to do load allocation, so it's pretty similar. And we looked at if we did SIME versus our own, and they're pretty close. So yeah, so just rescaling each load curve so that they match the feeder head. Plus any the true load of the feeder head. So taking into account all the PV on the circuit. And then like I said, we calculated the other feeders all kind of aggregate together and place them close to the substation transformer in the modeling. And then you get a bunch of output curves that you can simul import and apply for every hour of the simulation. And so next, we to do some of the PV modeling, we used this tool called PV Watts from NREL. They're now known as the National Laboratory of the Rockies. But it's a pretty cool tool because you can input a lot of the information, like system characteristics of the PVs. So DC to AC ratio, how much, what's the capacity, single axis tracking versus fixed tracking. There's a whole bunch of options. So it's a pretty powerful tool on helping to generate PV profiles. And we chose to use this instead of the actual solar data that we had from Excel because some of the future ones, obviously, we don't have data for those. And they're also all different, located in different geolocations. And one of the neat things about the NREL tool is they kind of have it, they split it up into different grids. So you can get different profiles based on different areas, different weather patterns and all that. So it's a pretty powerful tool. And I'll talk about, I guess, yeah, I mean, it pretty much explains it. It just generates an hourly profile for the whole year for the 8760 study. And we had to do this for some of the existing PVs, the future PVs, and as well as we did one for the FI PV and as well as all the aggregates, the aggregate PVs from the other circuits. So that's the PVs. And those were primarily the main focuses of the circuits. There was a lot of loads and there was a lot of PVs and not a whole much else in terms of DERs on this specific feeder that we looked at. So just to wrap up, yeah, we looked at some of the loads, some of the PVs for the DERs, and then what are our next steps? So we had to load all this data into SIME to actually perform the simulations. Yeah, and so FI is a flexible interconnect, if that wasn't made clear. Sorry about that. And so loaded into SIME, but then we needed to look at developing some study cases. So different scenarios that are possible, different modes of operation in terms of control modes for the FI to provide volt var support or volt watt support if it was necessary, and seeing kind of which one of these study cases provides the best kind of results to maintain performance while also minimizing energy curtailment. So some of the study cases we looked at, obviously we had the reference case, the case 0. So it's all the modeling except no FI, no flexible interconnect PV. And then we call that case 0. And then there's a 0.1, which we use to help with some of the voltage analysis. So which is no flexible interconnect and no other PV outputs. And then so case 1 is the flexible interconnect plant not controlled. So fixed power factor case is case 1. Case 2 talks about a lot of the different volt var or volt watt methods used, and those are actually based on the curves for those are based on IEEE 1547. So some of you might be familiar with how those look. But yeah, so case 2 is just no curtailment. Case 1 and 2 are no curtailment, but just different kind of control methods for the FI plant itself. And then case 3 and 4 kind of go into, now we're looking at some of the curtailment strategies that we might have to apply to eliminate some of these violations. Case 3 is doing it hourly. So for every hour of the year, 87, 84 hours, do we need to apply this curtailment? And then case 4, we split up into two different ones. One is the 12 dispatch profiles per month, and really that's dispatch profiles is a kind of a misnomer because it's more like limit curves. It's a limit curve basically. So you'll get basically a limit for each month of the year. And then the second part of case 4 is the seasonal weekend versus weekday kind of limit curves that would be applied to the FI. And for case 3 and for case 4, both of them, we only looked at the fixed power factor cases and the conservative volt var case, and we'll kind of show those results why later on. But as you can see, there's any number of permutations here between case 2 and then all these different 2A through D, and then case 3 and 4. So a couple different cases, but we looked at, we'll show some of the results in a couple slides here. So primarily looked at so the curtailment cases 3 and 4 were the most interesting because they eliminated a lot of the thermal violations as well as the voltage violations that maybe popped up through the introduction of the FI plant. And you'll see here, the key thing to note is the top row here, case 1, showing the PV plant's output throughout the whole year. And then if you want to compare that to case 3.1, 4.1, and 4.2, you can kind of see some of the energy curtailment that would be necessary in order to reduce these violations, as well as how much did we actually have to reduce the production of the plant by, how many hours, and how many hours of operation were curtailed in total. And so this is the fixed power factor case. You can kind of see between, so case 3.1 was the hourly. You kind of get less curtailment than you would through doing the case 4, which is the monthly or the seasonal. But doing it hourly, it's kind of a little more complex because of to implement versus having just a seasonal static season workday weekend or a monthly curve. So this is the fixed power factor case results, and yeah, I mean you can see the monthly. This 4.1 is the monthly limit curves and has the highest sort of curtailment there. And then the next case that I was mentioning is this conservative volt var, which eliminated, we wanted to, this is the most interesting one for this study because it reduced a lot of the voltage violations and thermal violations that, the circuit would see. So you can see here, the monthly version gets sort of this big curtailment. Looking at it seasonally, we get less. And then, of course, doing it hourly, we get the least, but it maybe didn't necessarily kind of, there's a trade-off in complexity of implementation. So, it's a decision the developer has to make with that. So, just interesting results. And then these are mostly the thermal violations, and then some of the voltage violations. Why would we not choose? You can see these graphs here. 2B has kind of these small percents of elements that are being affected by an overvoltage. 2D as well. But so why would we not choose those? And we didn't show the results of 2A through D, but they ended up having a lot of thermal violations along the feeder. So that's why those aren't really viable options when you compare them to 3.1, 4.1, and 4.2. And these percentages are kind of representing it's pretty much the probability that an element would experience a violation throughout the entire year based on previous hours and looking forward to the next hours. It's not really representing how much of an overvoltage it's experiencing, because that would be bad. Obviously, you don't want 94% overvoltage, but this 0.2% is pretty much the percentage probability that an element would experience some type of violation. And then you can see kind of how the curtailment from each case kind of stacks up against each other. You can see the monthly ones obviously have the highest, like I had mentioned. Seasonal ones are a little less, and then obviously the hourly ones, 3.1 and 3.1b, are kind of the lowest, but harder to implement. So how does this look, kind of when it's being applied? So this data is from one of the month of March from May, sorry, from the simulation showing, weekdays, weekends, and this is the hourly dispatch. So the light blue line, I don't know if it's hard to see up there, but it's kind of the original. It's the base case. What did the plant output at this hour of the day? And then you can see how the hourly dispatch, the hourly limits are applied to 3.1 and 3.1b here. And you can kind of see just the amount of curtailment necessary in order to keep the violations down. So this is an example of the hourly limits of being applied. What does it look like for the monthly limit curve? So along the x-axis here is months, and then the kind of on the y-axis is the kilowatt limit for the plant itself. So you'll see in the next slide, for the month of May, you get about 2,000 kilowatts for 4.1b, and it's like 2,500 kilowatts for 4.1. And you'll see that in action here, where, okay, now you see this original dispatch, and this is the same timeline as the hourly one. But yeah, you see the kind of original dispatch, and then, okay, how does it look if the limits are applied? And you can see these like flat curves for the FI plant. So that's how those look for the monthly limit profiles. How does it look for seasons? So obviously you have some more illustrations here just showing what is the output of the plant, what is the possible output for the plant during different seasons, and then weekday or weekend. You can see just similar in action. During the day when the PV is producing, you kind of get these limits being applied so that the violations don't happen. And then yeah, so that was for 4.2 and then 4.2b. And then you can see these in action here, being applied to, again, it's same illustration, the original base case versus some of the, how do those limits look like when they're applied to that curve. So good amount of curtailment, obviously, and you can see how it changes during weekdays and weekends, where loads might be different or generation might be different. So, and these next couple slides just kind of highlight what John was showing earlier, about the static kind of dispatching of the FI plant. And these are showing, it's a heat map showing kind of which hours of the day, which seasons or weekdays and weekends kind of experience the most curtailment, and its percentage of curtailment that's shown there. But the colors as well, the red is more curtailment, green is less. So you can just see how they compare for the different study cases that we looked at. maybe apply that to the different management systems that are out there. And yeah, these are all pretty similar. This is for now the monthly, but same idea. Red is more, green is less. Curtailment for the plant for different hours of the day and months of the year. So um, so yeah, just to conclude some of those results, we had to develop this methodology to kind of analyze the flexible interconnect PVs, and we're looking to do this for loads as well as well. So the results that we found was that the introduction of this plant actually does kind of introduce some thermal and voltage violations, and to eliminate them, we kind of looked at some of the worst limiting elements along the circuit, whether it's a conductor, transformer, any element voltage regulator that might be hitting its limits, and curtail the EFI plant to eliminate these violations based on those worst case limiting elements. And then to eliminate a lot of the voltage violations, if it wasn't, I don't think I mentioned it earlier, but those volt var controls really help to reduce the probability of voltage events occurring on elements. So those were kind of really impactful to look at the study, and that's kind of why we presented the results of the conservative volt var case, because it applied the best results to limit those voltage violations. And then as well as some of the other results that for obvious reasons we didn't want to include here in the slide, but we made recommendations for some of the components in the circuit that might be looking to need an upgrade in the future, for because they're pretty close to maybe hitting their limits. So yeah, just we made recommendations for future upgrades to consider within the feeder. And then, like I was talking about earlier, you can see how some of these study cases wrap up to different implementation complexity and different levels of energy curtailment, which is important for the developer to know, because obviously they want to minimize kind of both, right? Implementation complexity, they want to be simple, and energy curtailment, they want to be low. So yeah, that was some of the results. And then yeah, thank you.
Thanks so much, Mark. And then it's great news here. Basically, Mark shared with us your Volvar settings and the flash interconnection, they don't fight with each other. Indeed, if you implement a flash interconnection with the Volvar setting for the voltage control, it can both relieve the thermal constraints as well as the voltage violations, which is great news. Because I know a lot of developers and utility, they are concerned, if I do the flash interconnection, like, will that change or impact my the voltage Volvar control to mitigate my voltage issues? So at least from the planning study, Mark, walk through the exo energy case with flash interconnection. That's good news there, which is great. Thanks so much. With that, we have a small pause here. I need to go back to go to the QR code so you can see where you can scan it. Can log on. Just I think 4 questions there to just try to get your thoughts.
Can I ask one question, follow up on that?
Sure. How about that? We'll run the poll, and then we will take the more questions here. Let me see. If you could scan the QR code, and that would hopefully direct you to the second poll questions there. Maybe pause here a little bit to see if I can scan. While you are looking at the QR code, just want to also share what Mark walked through is a planning study for the flash interconnection. There are not working. Oh, sorry, bummer. Seems that the QR code doesn't work that well. How about this? Let me just do quickly walk through the 4 questions I have here for you. This is a lot of slides to flip. Appreciate all the effort. So which application scenario will you consider for flex interconnection? It's a flexible load interconnection, or you will do the flexible DR interconnection, or do both. How about that? Will you be consider the flexible load interconnection? If you, yes, raise your hand. See the value? Yeah? Half of the people will see the value for the load interconnection. Then how about the DR interconnection? More than half. Great. That basically means that the extra energy, you have more work to do then. The second question here is, what else would you like to learn more about a flex interconnection? The first, select all that applies. The first option here is more utility demonstration projects with flexible interconnection deployment experience. For this question, I want to share at this moment in the US, there have been a few demonstration projects managed by 2 utilities. One is Avangrid in the northeastern US. The other one is ComEd in Illinois. And indeed, ESIG is trying to work on a white paper to summarize their experience. So stay tuned. More details will come. But definitely, if this is aligned with your thought, definitely will do that. Okay, how about this? If you want to see more utility demonstration project with the flex interconnection deployment experience, can you raise your hand? Yeah, half of the people. That's pretty good. How about the second one? The benefit cost analysis of a flex interconnection from developer perspective. Good. By the way, from the utility perspective, if the developer doesn't buy in, you cannot have the flex interconnection. Is that right, Zach?
See this on. Yeah, I think one of the challenges we have, so on the load side, it makes a ton of sense. As I said before, it helps put more kilowatt hours to the system, which can help with downward pressure and rates. We're not really sure on the developer side. I mean, there's a clear benefit for developers in terms of reducing costs and getting online faster. But from a general societal perspective and a customer perspective, the benefits are a little bit more nebulous for the DER generation interconnections for flexible interconnection.
Thanks. The third one here is, do you want to know more about the technical details about flex interconnection controllers? How the utility set up the threshold and how the DERs will be curtailed? If you are interested in that, come on. Oh, that's a lot of interest here. As I said, the white paper, ESIG white paper will talk about this then. How about the tariff and the rate structure? Wow, this is a really great audience. I can't anticipate better. Exactly. All the I see that all the hands already. So definitely seems that we need to do a lot of work and try to cover all the interesting points here in our ESIG white paper. I need to leverage our experts here and also your experience and on this topic. How about the next question? That's a fun question here. What are your concerns with adoption of a flex interconnection? The first one here is the DER curtailment uncertainty. Are you concerned about this question? If you are, raise your hand, sorry. I can tell you that if you are the developers, this is the #1 concern they have. Because at upstate New York State, we run the flex interconnection workshop with all the developers. This is the #1 pick for them. How about the second question? How about the load curtailment uncertainty? Are you concerned? Raise your hand if you are. Yes? Good. The third question is a more technical. Basically, when we do the flex interconnection, when you have the centralized controllers, the centralized controller need to talk to the local controller for the load and for the DERs. Then the one scenario here is, what if the communication network doesn't work as expected? And usually for the flex interconnection, we call it fail-safe mode. What it means there is, if you lose the communication, you need to have some sort of a protection scheme to make sure even you lose the communication, your grid asset will not be overloaded. Otherwise, the ZAC will say, hey, sorry, we don't have the phase 2 of the flash interconnection anymore. So my question here to you is, are you concerned about the loss of communication in flash interconnection? If you are, raise your hand. Okay, a good amount of audience here are concerned about that. How about this one? The fourth option here is it depends on utility. Some utility will say, hey, you know what? If I use the terms to manage your flash interconnection, it's an additional staff and equipment cost. So usually, if you avoid upfront the capital cost for grid enforcement, but the utility said, okay, well, I charge a small amount to manage the terms to control your DER or load for flash interconnection. So my question here is, will you be concerned about additional charge from the utility to manage the flash interconnection program? If you are, raise your hand. Okay, decent amount of interest. How about the regulatory part? If you are from the commissioners, indeed, this is also one of the good challenges we have, how to get this one into the regulatory approval. Yes, you're interested. Thanks so much. Seems like all these questions has a lot of interest in this. As I said, we have a lot of work to do. And then not only we have a work to do, I would love to hear your thoughts, your feedback, your contribution even. So basically, as I said, the ESIG is trying to work on a white paper focus on the increasing DR load, hosting capacity. The technology will go beyond even flash interconnection. Flash interconnection will be one of the key technology there for the potential white paper. I will circulate with all the people who attend the tutorial here to try to get your thoughts on that. If you're interested, we welcome your participation. Indeed, that is the last questions I have. And we do have 7 minutes here. I want to open the floor to capture your questions that has not been addressed. All right, good morning, guys. It's 10:32. Maybe we should keep the ball rolling here. If you're not seated, please be seated. So in the first section, we'll talk about a flash interconnection. One of the potential concern about a flash interconnection is really the curtailment. So we call it as a little bit invasive. And then the second half, we will talk about the power flow control. This technology is not invasive. Basically, you don't really need to deal with any of the curtailment. The developers usually will feel better when there's no curtailment involved. So with that, I will pass it on to Michael Hannestad from RLC Engineering to talk about the grid flow control technology and their experience working with the utilities and how the technology is pilot and demonstrated in the field. What is the lesson learned? All right, with that, I will transition to the Michael.
Thank you, Leo. Yes. Yeah. Hopefully, I'll figure out this mic throughout this presentation. Just yell at me if I'm way too quiet. That's fine too. I appreciate, John, Zach, and Mark going first because they really set the stage well for this. So when we're looking at grid flow controllers, let's see if this works. There we go. Give a second. Let's make sure this is still okay. Perfect. So when we're thinking about grid flow controllers, for this discussion anyway, we'll be thinking about power exchange from phase to phase. And why is that needed? So the previous discussion looked a lot at how to increase hosting capacity through control of the DER or load itself. So how to manage that operation to get more of those things online. In this case, we're going to look at systems that have imbalance, as many distribution systems do, and how we might be able to create a more balanced system in order to remove some of the constraints, such as worst phase thermal constraints. So if you have one heavily loaded phase, you're going to likely run into the thermal constraint first on that phase. But similarly, if we're looking at this example here, if we think of a phase at the top, we can see that that's most heavily loaded. We're going to run into likely thermal issues first there, but also low voltage conditions are most likely to occur first there as well. In this case, if we consider B to be the next one down, that's the most lightly loaded phase. Unlikely to hit thermal concerns there, but we might hit high voltages. So now we have this situation where different phases might be limiting under different conditions. So the power flow controller that we're going to be talking about is made by Switch Source. It is a 3-phase shunt connected power electronics device. And what it does is it dynamically balances real and reactive power upstream of the device because it is shunt connected. So downstream of the device, you will still see unbalanced power because the loads downstream of it are unbalanced. But it will sit there shunt connected, look at the imbalance in the system, balance at that point, and then the upstream system appears more balanced. Now, just as a graphic showing that, the right side of the system would be that downstream system. So it is the system where you can see that heavy A phase and light B phase. You have the phase EQ, the power flow controller, in the middle, and then upstream of it, the system appears more balanced. You can see A phase is still a little bit heavier, but B phase has come up a lot. And C phase is more in line with them as well. So it is resolving the upstream unbalance. Getting into some device specifications here. The current rating of this device is 133 amps. It's about 45 amps per phase. It's a 15 kV class device, and it's typically deployed on Y systems as it acts on zero sequence current. It is a pad-mounted device. The dimensions are here. It's about 4 feet wide, 11 feet long, and 5 feet tall, and it weighs about 9,000 pounds. And this is a fun slide, unless you don't like phasers. So the leftmost panel here is the unbalanced phase currents. So these are the currents that you might see, or the current phasers that you might see out on the system. In panel number 2, it is just phasor summation. So we're summing the A, B, and C phasers, and you get a resulting neutral current from that operation. So that's indicated by that black vector there. In panel 3, it shows what the power flow controller is actually doing. So what the power flow controller control objective is to eliminate the zero sequence current that's being measured wherever it's being installed. So it is injecting a counter zero sequence current. It's measuring the neutral current, essentially dividing that by 3 and injecting a counter current opposite of what it measured. This shifts your phase currents. So now your A, B, and C phasers have been kind of rotated and the magnitudes have shifted slightly, such that if we move over to the rightmost panel, you can see that after you sum these new phase currents, you've eliminated that zero sequence component or significantly reduced it if you are exceeding the ratings of the device. And this is an example from a utility circuit out in the Midwest. This is before the device has been added to the system. You can see it's very unbalanced. C phase is very heavily loaded. B phase is light, and then A phase is kind of in the middle. You do your phasor addition, you end up with about 120 amps of neutral current. You add the device, and things are shifted slightly. Your magnitudes are much more balanced, but when you do the kind of corrected phasor addition, your neutral current has come down near zero. We're at about 1.2 amps. And this is another graphic that's really just trying to drive that home, where, again, if you look at the rightmost portion of this graphic, Yeah, just double checking that it's right for both of us. It was a long night. So on the rightmost of the, or right side of this power flow controller, you can see that you are still seeing the system in balance. It looks a lot like the pre-existing condition without the device. You have your heavy C phase. If you do your phasor addition, you still have your neutral current downstream of the device. But upstream of the device, things look more balanced. Now, what the device is doing, we said that it does that zero sequence current injection in each phase. What that ends up actually looking like is power transfer between the phases. So if you had a really heavy C phase, you can see what the device is actually doing is it's injecting power into the C phase. A and B were both lighter. B was the lightest. You can see that it's pulling most of that power from B phase and a little bit of power from A phase. So what that looks like is your A phase got a little bit heavier, your B phase got a lot heavier, and your C phase got lighter. So it is balancing out the power flow in each of those by exchanging power between the phases. And that power exchange is happening based upon that zero sequence current injection. All right, so we talked a little bit about what the device was, its specifications, how it works. This is how we end up modeling it. And it's actually how RLC got involved. The manufacturer approached us and asked, how can we actually simulate the performance of this device? And we developed this model. And it's fairly straightforward. We use a Python interface that runs a load flow, collects voltage and current information similar to what the device would be measuring in the field. And then it passes that current and voltage information to the controller that the manufacturer uses. And that controller determines what the device is actually going to do. Those P and Q values that the manufacturer controller outputs gets passed to essentially back to our Python interface and gets assigned to a representation. Now, the representation changes depending on the software. In SIME, we use the battery energy storage system, the BEST block. And that's because it gives us a Python device control script hook that's a little bit more convenient and runs on every single iteration. And that's pretty helpful. But it works just as well in Synergy. It's just implemented slightly different. Rather than being implemented on every single iteration, we just run a load flow, gather the data, and then adjust spot loads, either positive or negative. You can still use your PQ assignments the exact same way as a battery, which is just going to be charging or discharging in SIME. So everything stays the same, just a slight tweak on the front end and how it kind of operates, but it's still just PQ assignments. Okay. So now we know how we're modeling it. What are the system benefits? And this really gets back to what was just previously discussed. Typically, what we see is thermal or voltage constraints when we're thinking about hosting capacity. There are others, but those are pretty large primary ones. When we look at hosting capacity maps, that is very common on what everything is being based upon. And as we discussed with this device, it is being injected into systems with imbalance, which means from a thermal perspective, you likely have a limiting phase condition. It's just more heavily loaded than your other phases. From a voltage perspective, you might have that one heavily loaded phase, as I said, or you might have a lightly loaded phase. But essentially what's happening is you are dragging unbalanced current through impedance, and it's causing a fanning effect of your voltages within your system. Your lightest loaded phase is going to be getting higher. Your heavily loaded phase is going to be getting lower faster, and you're just end up with a lot of voltage imbalance. Your voltages will fan out, which is what you see kind of in that top plot. The maximum voltage imbalance there was 2.6%. After adding the device, you've balanced your power flows upstream of the device. Therefore, your voltage drop phase to phase to phase is essentially equal. So now you've pulled your voltage profile closer together as you move downstream, at least until you hit the device, because you have to remember that below the device, that imbalance still exists. So you will still accumulate your voltage drop at different rates below the device. But because you've eliminated everywhere upstream, you end up with this kind of global benefit, which we'll see in a minute. But in this example, we saw it decrease from 2.6% down to 1.1%. Okay. So actually, skip 2 bullets. One benefit is that this dynamically regulates. So it's a power electronics device. It's constantly monitoring the system, and it is updating pretty quickly in the seconds time frame. So it is going to be operating much faster than voltage regulators and other things on the system. And it's going to help smooth out all of those transitions and imbalance. And obviously, because its primary objective is to reduce zero sequence current, it's also reducing your neutral current within the system. So because this acts on imbalance within the system, one of the challenges that you have to do is decide, is it a good system to deploy this device? There are different levels that you'll go through, but the level I'm showing here is kind of that high level screening. How do you know if you have 1,000 circuits, which circuits are a good fit for this device? And the method that I like to use is, or I would say the easiest method, we'll start there, is to just look at your feeder head and neutral current. It's a pretty easy thing to pull. A lot of people have data at this particular point. So you can use that as a pretty quick metric where you can just pull it across all your feeders and say, okay, we at least know that these ones have quite a bit of imbalance. If you can get more detailed than that, it's also interesting to start gathering, okay, we know what it is at the feeder head. What is your neutral current just maximally on that circuit? Similarly, if you can get that data, what is your voltage imbalance maximally on that circuit? Because you could have a lot of imbalance, but it could be a short circuit with large conductors, and it really doesn't manifest in a whole lot other than you have some high neutral current. Maybe that's not the best fit for it. But if it's a rural circuit and you have one, it's long, two, it's imbalanced, you can get significant amounts of voltage imbalance showing up. And that's when you can start to really parse out where you want to put the device. And another one that I like to use is just your count of high voltage conditions and low voltage conditions, because that lets you know if there is an actual problem that you could be solving with this device. Going the wrong way. There we go. So circuit selection. Once you've screened down through all of your viable candidates, you've said, okay, these ones look like they might be good places to stick to the device. Then you can get into actual site selection. So look at those individual circuits. My favorite way to do that is to create heat maps. So here is a depiction of 2 heat maps I generated. One is for current imbalance, actually specifically neutral current, and the other is voltage imbalance. And if you see, okay, so you can see the cursor. If we're moving down this backbone path, you can see that it is colored. Thank you, Leo. You can see that a bit better. Perfect. You can see that right around where Leo's cursor is, we have this red or orangey condition. That means we're right around 150 amps of neutral current for this circuit. And you can just see approximately where that drops off. And then on the right side, I can take over if you want. Thank you. You can see that voltage imbalance accumulates as you move down the feeder. And that makes a lot of sense based on what we were just talking about. You're dragging unbalanced current flow through impedance. Your voltages are just spreading out and fanning apart. So you're near the end of the feeder, you've accumulated quite a lot of voltage imbalance. And what you want to do when selecting a circuit here is, one, place it where there is quite a bit of imbalance. So you want neutral current to be there because that's really the source that it's using to correct for the imbalance. But you also want to put it far enough out on the system that you are maximizing the distance for which you're balancing, because that's what's closing that fanning effect of voltages across your system. So the greater distance over which you're balancing your power flows, the better performance you're going to get. So looking at that, you can see that for this particular substation, those phase voltage is really fanned out. And on the left, we still see that voltage profile. It kind of got worse, 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 worse. And then it declined a little bit because we peeled off enough power that the flows began looking a little bit more balanced. And you'll see that sometimes. Occasionally it'll look very balanced at the substation, but all of a sudden you hit this one lateral that peels off an incredible amount of load. And now right after that point, you see a very unbalanced system because the rest of it, the system's, it's not balanced. You peeled off a bunch of that load. Similarly, you can have a lot of imbalance at the substation. You hit a lateral, and all of a sudden, your heaviest phase fell in line with your other ones, and your neutral current drops off. So looking at it with this type of heat map gives you a very intuitive grasp of what that imbalance looks like throughout your system and where you might want to put the device. And then similarly, we know we want to push it as close to that area of highest in voltage imbalance as we can because we're maximizing the area that we're correcting over. So then we can look at the simulated performance of the device. On the left, we have without the power flow controller. So we still see the neutral current going all the way down the circuit. But on the right, we have the power flow controller on. And what we immediately see is that the neutral current from the feeder all the way down to where the device is specified, it's turned to that blue color, which means it's dropped from about 150 amps down to maybe 20 or 30 amps. So we're maximally utilizing this device. And that's a good thing to note here is that the device doesn't get overloaded per se. It will correct up to its highest rating and then it will stop. So if you have 150 amps of neutral current on there, it's going to clear up 130 and it's just going to leave the rest on the system because it's not rated to do that. So the other thing that's really showing up here is noting that it is shunt connected. So below it, the imbalance exists, but above it, you have kind of corrected for that imbalance. Now, I think the voltage results tend to be a little bit more fun because they're a little bit more stark. You can see on the left, again, it's the one that you saw before. As you get down towards the end of the circuit, you end up with a very high voltage imbalance. It was actually simulated as in the 4 to 5% range. After the device is added, you can see upstream, you're fairly close to the source. The voltage imbalance isn't as extreme because you're in a stiffer part of the system. But because you have kind of equalized the voltage drop above that device for about half of your circuit, you can see that the voltage imbalance dropped dramatically below where the device is being located. So it is pulling your whole voltage profile together. You see it slightly less in the graphic above it. You can see that they were shifted lower towards that 0 to 1% range. But downstream in that 5% range, or what was 5%, it's really dropped to about 2.5 now. So we've cut that voltage imbalance in half by equalizing the voltage drop among your phases. So here we saw the max was 5.4%. It was dropped to about 2.6%. And we can see some of the other metrics down in the little box where the feeder head neutral current dropped from 124 amps to 14 amps. It was a 110 amp reduction. The local neutral current was 132 amps where the device was placed. That was completely eliminated. It was within the range of the device capability, which was 133 amps. And then again, maximum voltage drop was pretty much cut in half, a little bit more. So if we stay on this slide for just a second. Now, what that's going to do is from a DER hosting capacity perspective, kind of taking it back to the topic of this, you can see that I think it was B phase in green prior to the device would have been incredibly limiting. I mean, some of these were just right on 126, so 105% already. Essentially couldn't add anything to that phase. It would have been limiting. So either single phase installations or 3-phase, you would have been running up against that. And then in this case, we can see that before the device, actually both A and C phase were pretty close to being a limit. They were both at about 95%. After you added the device, it really helped your most heavily loaded phase condition. It put a lot of, essentially it pulled a lot of power off of one of the phases. It looks like C phase in this case. It was likely heavier loaded. So it pulled a lot of power off of C phase and it dumped it all on B phase to correct for the imbalance in the system. What that ended up doing was it left B phase largely untouched. And because it left it largely untouched, it didn't really resolve the limiting, what would have been a loading condition on B phase. So if you added more load on B phase, you would have gotten more voltage drop. You would have still run up against that one, but it really helped your high voltage limit there. Okay, so that was the simulated performance. We're transitioning now into field results. So this was part of a pilot. It was done in the Georgia Power area. The scope was identify circuits, run the simulations, and then field test the device. And one of the objectives of the Georgia Power was to look at different control modes. Ultimately, how the device operates is essentially the same. You're shifting power phase to phase. The control objective changed slightly. In the current control mode, it was looking at zero sequence current. In the voltage control mode, it was looking at zero sequence voltage. So slightly different control modes. They wanted to compare the performance benefits of the two. But ultimately, if you're just trying to kind of get your head wrapped around what the device is doing, it's still shifting power phase to phase. It was just a control objective that changed. And then we looked at this in two different ways, a snapshot comparison, and then performance based upon load level as well. So the snapshot's what you might expect. Took a snapshot of the system without the device, with the device in current control mode, and with the device in voltage, and compared the performance. And then versus load level, you'll see there are graphs where we looked at a range of loading conditions and then looked at the performance under each of those loading conditions with a scatter plot. So the purpose of this table right here was simply to baseline the snapshots that we were using. Are we actually comparing apples to apples here? Because if you're taking a snapshot, you want to make sure that the results that you're pulling are actually comparable. So if you're looking at the loading conditions from each of these, we can see at the feeder head, they were pretty similarly loaded. So that's that first column. And then A, B, and C phase, they were all fairly in line as well, because these were all taken, you can see, at different months and days. And then neutral currents were all essentially in line, 144 to 145 amps. And these are at downstream meters now. And the apparent power, again, pretty consistent across the board. So looking at both the feeder head and a downstream meter point, we can see that these conditions were fairly well matched and should be a good candidate for kind of the performance comparison that we were going for between control modes. And then this is what the field results showed. Without going through everything here and kind of focusing more on the voltage mode reduction and current mode reduction, we see that in voltage mode, we resolved 102 amps at the feeder head. In current control mode, we resolved 89. Feeder imbalance was reduced by 10.1% in voltage control mode and 9.3% in current. Voltage imbalance, so this is as measured at the feeder head. It was a 0.5% reduction and 0.4%. You typically don't see as much of that reduction at the feeder head because your voltages are already pretty tight. At the upstream meter, we see that voltage imbalance be more pronounced, a 1.2 to 1.4% reduction. So it was going from 3.7% and it was dropped down to 2.5. The upstream current imbalance, that was brought from 38.1% with the device off to 23.6 in voltage mode and 25.6 in current mode. So about 14.5% reduction for that voltage control mode. And again, neutral current was dropped by 97 amps in voltage and 85 in current. The downstream meter here, it did not have it's not impacted by the device, again, because this is shunt connected. So the only impacts that you would expect to see are in voltage, and they aligned pretty well with that upstream meter. So about a 1.1% reduction. Okay, so these I thought were interesting because they weren't how I would typically visualize performance across a system. And what it reflects is, in this case, at the feeder head, what is the neutral current for different load levels across a period of time. So I think it was about 6 months that we were looking at. So with 6 months of data, where did all of your loading values fall? And what was the corresponding neutral current? And the device was operated in 3 different modes: device off, device in current control mode, and device in voltage control mode. So when the device is off, you kind of get a fairly linear relationship here, where you can see as the load increases, your imbalance also increased. You saw this linear increase in your neutral current. Once you added the device, it flattened it quite a lot. So now we had, you drew a midline, about 20 amps of feeder head neutral current across the load levels. And there was a slight uptick right near the end where you were probably leveraging quite a lot of the device. You might have been maxing it out. And those conditions reflected where you started to hit that more linear increase again. Similar story with the feeder head recloser current imbalance versus loading. Off, you have high imbalance, and then when you turned it on, both the current and voltage performed pretty similarly. It looks like voltage outperformed it a little bit, and that's what the snapshots showed as well. So it's essentially what we expected. And it dropped it around 10 to 11%, I think, which is also what the snapshots tended to show. Midline story is pretty much the same, a little bit more pronounced. You can see that very linear scaling of your neutral current versus your load. The neutral current for the current control mode and the voltage control mode tend to be pretty interesting here, because you definitely see in the voltage control mode a point where you are really suppressing your neutral current, and then you are likely maximally utilizing your device, and then it hits more of that linear trajectory, just like when the device is offline. So you're hitting the device limit, it has corrected for it up to that point, and then the system just responds normally beyond that. And again, this is the same story. It is mostly flat, and then it just kind of knocks it down, about 10%, 10 to 15% for your current imbalance versus loading. Voltage imbalance versus loading, a little bit harder to see, but you are reducing it by about that 1.1% that we saw, going from 3 to 3.5% down to about 2.3 to 2.5%. And the conclusions of the pilot study, it validated that it was able to dynamically balance the system. Both control modes significantly reduce your neutral currents, current imbalance, and voltage imbalance under the real world conditions. Voltage control mode performed best at this location. It's not necessarily true that voltage control mode will always perform best, but it was interesting to see that they performed fairly neck and neck across those. The neutral current decrease, 85 to 100 amps. Voltage imbalance reduced by about 1.2%. Thermal capacity increased by about 9%. And that 660 kilowatts corresponds to approximately the 45 amps per phase rating of the device. So it's 133 total, but about 45 amps per phase. And that it helped kind of up to that limit. And the performance was very similar to what we saw in our SIME simulations, which kind of validated that the simulations are a good approximation of what is happening out in the field, which is always gives that warm, fuzzy feeling. So in this case, the power flow controller demonstrated strong potential for unlocking some of that capacity in the system that's otherwise tied up by just simply there being imbalances in the way the system is being operated, because it is being held back by whatever your limiting condition is. Oftentimes, that is a single phase element on either voltage or thermal, whether it is high voltage, low voltage, or just pushing too many amps through one of your phases. So another thing that was done with this particular circuit and pilot was assessing hosting capacity benefits from a PV or an energy storage perspective. And it was more residential adoption of PV or energy storage. So it was, okay, you have these kind of single phase communities, laterals out on a system. If you started to get higher penetration of PV in some of those single phase areas so that it is an unbalanced adoption of these, how would the device perhaps help with this? Because it's going to help both from a load perspective, but also a generation perspective. And also because it dynamically balances, if you had a high penetration of residential that is fluctuating with, let's say, just clouds or whatever the case might be, it is going to dynamically adjust in the seconds period, similar to what the PV is doing, and it will help to smooth out that, and it'll transfer that power phase to phase to make the system look more balanced throughout those transitions. Okay. So blue is before, red is after, and since we're looking at hosting capacity values, the higher value is the better value. So in this case, we're looking at single phase PV adoption on either A, B, or C. And we can see that before the device, we could get about 400 kilowatts on A. After the device, we were able to get 575. On B, we were only able to get 175 kilowatts of PV on before the device and 425 after. And that makes a lot of sense if we think back to the voltage profiles we were looking at, where that B phase was very high without the device online. So if you did not have the power flow controller online, B phase was right up near 105%. It makes sense that that would be the most limiting condition for being able to accommodate additional PV. And then once you add the device in, it brought that way down. So we tend to see a very large increase there. And then similarly on C phase, we can see that it was 325 kilowatts and that went up to 650. So that one doubled. Very similar story again on energy storage. We couldn't get hardly anything on A phase, maybe one house. And that went up to 275 kilowatts after the device. B phase, a little more than doubled, it looks like, from 625 up to 1300. And then C phase, again, a little more than doubled, 250 to 625. So we saw increases in that hosting capacity capability. This is really just a summary. So it's summarizing both the power quality benefits that were observed for the site, where we had 109 amp reduction in neutral current. We had 133 amp reduction locally. So that was at the feeder head. This is local to the device, so about mid-circuit. And then the maximum voltage imbalance was about 50%, cutting it from 5.4 down to 2.6. And then we see those hosting capacity benefits spelled out again. So we're very good on time here. I've been kind of flying through this, but the BCA is always an interesting one. I will admit that I did not conduct the BCA. The BCA was done between SwitchSource, which is the manufacturer of this device, and one of the pilot utilities, in this case, NGrid. So SwitchSource and NGrid worked on this BCA. They worked out how much kind of value would be assigned to each of these categories. So capacity, upgrade deferral, that's essentially capacity unlocked above what was in the original system. Upgrade deferral, high annual imbalance, high seasonal imbalance. So that might be things like having to roll out trucks to recap circuits multiple times, kind of seasonally during a year, in order to resolve the imbalance conditions that were kind of moving throughout those years. Resolving power quality issues, DG integration, or volt bar optimization applications. Some things, conclusions to kind of draw from this. The maximum payback period that was observed during this BCA analysis was about 6 years. You can see that for upgrade deferral, it was 0, which essentially meant that I want to say that the particular scenario was looking at eliminating a mile of 3-phase line extension. So if you had one long single-phase lateral, no matter where you moved it, you were essentially shifting your imbalance around. The solution there, build out 2 more lines. The device was a clear winner. It was just cheaper than what that solution was. So that's why the years to payback there was 0. Similarly, if we look, or rather, just if we look down at the NPV cost assumptions, this is in 2021 dollars, but the retail cost of the device was $275K. There was an estimated $50K installation for the pad, getting everything out on site, and then a $20K maintenance around year 11. I believe this is the device that has a 20-year lifespan. And another kind of important aspect to this device, which some people question, is like, how long does it take to deploy? And usually it's about a day to kind of do the commissioning and dropping it on site. As long as the pad is already there, they can drop it and commission it pretty quickly. And it just is, pulling some lines down from the line, the riser goes underground, and then terminating them on the device, and it tends to go pretty quick. Okay. So power flow controller for grid reconfiguration. So the device does not have to stop operating during a grid reconfiguration, and actually it will often ride through it as long as your voltages are pretty well maintained. So this was actually an unplanned grid reconfiguration, and they didn't know, obviously, it was going to happen. So they just swapped the circuit over. You can see on your kind of top plots here, we had all of your phase currents across 2 circuits. So there should be about 6 lines there. And then at the beginning of the grid reconfiguration, one of your circuits is dropping to 0, and it's getting backed up by the other circuit here, which is why we essentially see the currents on that circuit double. So during this time period, on the middle set of plots, we see what the power flow converter currents are doing. And we can see that they jump up during that grid configuration because it saw more imbalance within the system. And then near the end there, we can see it kind of ramps up, which means that the imbalance increased in the system and it continued to ramp up. And then the system kind of gets reconfigured and it transitions back down to normal. Now on the bottom, we're looking at percent imbalance on those circuits. And in particular, they're looking at the percent imbalance on the circuit that this device is not normally on. So before the grid reconfiguration, the percent imbalance on this other circuit was about 15.7%. After that grid reconfiguration, when they're both being kind of served below the device, it drops down to 10.7%. And then at the end of the grid reconfiguration, when you return to normal, that average goes back up to 19. So it was cleaning up the imbalance even, well, from an average perspective, more than what was seen either before or after. I'll make you stand awkwardly for 1 second. So one other benefit that I wanted to mention relative to kind of hosting capacity is you are resolving the imbalance. And we talked about some of the primary benefits. And those primary benefits had to do with generally thermal and voltage control. But there are numerous secondary benefits to that, because as you kind of pull your voltages close together, a lot of systems get a little bit more efficient. So if you have VVO schemes that are in place, they're going to benefit from that tighter voltage profile. But similarly, from a volt var perspective, from DER, let's say, because many DER are operating based upon the average voltage measured, if you are running into a scenario where you're limited by one phase, you're essentially having to suppress the voltage of all three phases in order to mitigate that. So as you pull your voltages closer together, you don't have to consume as much reactive power. So if we think about that EPRI paper, one, you have leveraged more of your system by eliminating some of that imbalance. So your unconstrained region of your system has just gotten larger. But similarly, you are also optimizing your volt var region or your voltage control region. So now your unconstrained region got larger, but so did your kind of voltage region, where you can do a little bit more by consuming less reactive power because that highest voltage isn't really there. So it can help both three-phase DER in that perspective, as well as single phase, which is what we kind of demonstrated on this slide. And now I think you can get up without it.
All right, fantastic. That's great news. That seems like the power flow controller is very effective, particularly if the payback time is less than 6 years under all the conditions. That's very good news compared to the lifetime of the device, which is 20 years. I think there's one question you didn't answer. What is the power losses of the device? That is the utility concern, right? If you deploy the additional device in my system, the power loss is basically utility to recover it. That will impact all the electricity rate for all the customers. What, do you know anything about that?
A little.
Okay.
So we do model the power losses when we run these simulations. What we found tends to be that by eliminating some of that imbalance in the system, you tend to cancel out the losses of the device. So if you're trying, we had looked at a lot of studies that looked at the potential of the device to essentially reduce system losses. And they do a little, which means that they're essentially canceling out what they've consumed and a little bit more. But it was never, I would say, so prominent that it should be introduced as a benefit of the device. It's just, yeah, you are removing some of the imbalance in the system and you are getting some benefits there. I want to say that it's on the order of like 15 kilowatts of losses in the system or loss to the system, but it's really just the ancillary power electronics consumption, what the device is consuming to power itself.
Fantastic. Just wanted everyone to know I'm a power engineer by training. I love to talk about the balancing issues. In general, the system is more balanced. When Thomas Edison designed a power grid, we want to make sure the load is balanced among the three phases. The more balanced system, the neutral current will be smaller, the power losses will be smaller. I love to talk about that topic. Basically, that's what the power flow control, this device will do. Trying to balance the three-phase current and the voltage, make the system balanced, the power losses will be reduced, which is great. Let me run a few like the poll questions. I know the poll link doesn't work that well. I will just use the traditional way, raise your hands and like that. You can see that this shunt device is really trying to balance the system. And I have to mention one thing. Different utility has a different criteria for imbalancing. And for different circuit, your grid imbalancing is also different. So my first question here is, what is the current I current imbalancing criterion in your distribution planning, if you know it? Anyone? So this one must be the utility guys, folks would know better. But I just created some of the options here, 0% to 5%, or it's from 5% to 10%, or it's from 10% to 15%, or it's from 15% to 20%. So what it means here is, if I like Mike said, at a feeder head, you have all the sensors to measure each phase, the voltage and current there. If they get the fetch the data to the utility, they calculate it and they say, hey, you know what? The imbalance is too large. I need some take actions into my planning. And what is the current imbalance criteria that in the distribution planning? Anyone knows the answer? Or if you can step back into the mic, that would be great. Thanks so much. And say your name for your organization, that would be even better.
Hello. Thanks. First, I'd like to thank the panelists, but my name is Orland Whitney. I'm with the New Mexico Public Regulation Commission. My background is power engineering and controls. This is great. I just wanted to say, as my perspective here in New Mexico, here, let me see if I can, a little too tall for this thing. So again, I'm Orland. I'm with the New Mexico Public Regulation Commission. What I'm seeing here is at the top, you're 0 to 5%. That's mature telemetry, I'd say. And now at the bottom, you have something more unreliable. I think New Mexico is about 10 to 15%.
Wow, that's the middle point is sweet spot. So the ideal here, if you want to get a 0%, that's ideal. That's perfect. But the reality is in distribution is a lot of unbalancing, because when you have your house, when you have an EV charging station at your house, unfortunately, sometimes they create more imbalances. Is that right?
Yes, absolutely. And I think, one example we can look at for energy imbalancing for high penetration of renewables and IBRs is Portugal and Spain. And I think that's a terrific example that should be explained. And from my perspective, that was overly conservative inverter controls. And so I'd like to know your perspectives on that as well.
Unfortunately, I wish that I live in there, but I don't have the answer for you. But we can dig it out. So ESIG has launched the international initiative. We are engaged with more of the European peers. So I will keep that question in mind. Hopefully, I will answer that question.
Excellent. Yeah, just wanted to say thank you again.
Yeah, I really appreciate it. Any other folks want to share your experience about what's the current imbalance criteria in the distribution planning? Exo Energy, do you have any words?
Yeah, I don't know what our spec. I'd have to go look at our design specification guide or our technical guidelines, but I think part of it too is like we encounter it and figure it out as we come across it. So
sounds like I give him a homework. I don't know if you guys know that I'm a professor as well. I give Zach a homework to take home, and the next time you will answer the question to me and then. All right. So I know that different utility currently has different criteria here. I think as the gentleman pointed out, 10 to 15% is pretty typical. But think about that. 15% is a little concerning to me, because you think about it in the distribution systems, one phase is way higher than the other phase by 15%. And if that phase is overloaded, unfortunately, the utility needs to say, hey, how should I relieve the congestions? Either will be doing a manually trying to hook up some of the customer to another phase, move from one phase to another phase, or you can deploy the shunt devices here to manage the power flow. So it depends on what your option you will have or you would like to try. Then the second question, where do you see the application of the power flow controllers? And I do have 4 options for you to select from. One is you see the shunt device or power flow controllers that Mike talked about is trying to mitigate the phase current imbalance. If you consider that as an application, can you raise your hand? The current imbalance management. Yeah? Okay. That doesn't click that well. How about indeed, the first and the second, indeed, is the same question. How about the third one? Reduce the voltage violation. Will you see that application? If you are seeing that the power flow controller can help with that, raise your hand. Yes? Voltage is more, since I'm more appealing then, it's more attractive. And I think your conclusion is that voltage control is more effective than the current control. Is that right?
For that one, but they were both eliminating the same imbalance. So
okay. So basically, Mike doesn't have the mic here. His answer here is it's for that circuit, the voltage control mode for the shunt device is more effective, but at the end, roughly the similar. So you manage the voltage imbalancing, that also will eliminate the current imbalancing. So basically, you have the shunt device that will mitigate the imbalance of the voltage and current simultaneously. Right. How about the next question? Where else do you want to learn more about flow controllers? So like all that apply. The first one is the more utility demonstration project was a deployment experience. I have to say that Mike talked about the Georgia Power, and also he showed some experience about the national grid. He talked about NGrid. NGrid is short for national grid, by the way. So both from the southern part of the US and to the northeast of the US, at least from the pilot project there, they see the potential of the technology to help with the imbalance management that could increase the DR hosting capacity, that could increase the load hosting capacity. They can mitigate the imbalance and trying to avoid unnecessary grid upgrade. So if you are interested in trying to know more about the utility demonstration project with deployment experience, can you raise your hand? Okay, good. And Mike showed one example about benefit of cost analysis as BCA, as he talked about, from the utility national grid, that the pilot project. Do you want to see more benefit of cost analysis from more utilities? If you're interested in that, raise your hand, please. Okay. How about the third options? Do you want to know more about the technical specs of the flow controllers? The Mike did a fantastic job. You can see that it's all about imbalance the current voltage, trying to balance it. But of course, there's all the power electronics devices and how the device is controlled. And if you know more about the technology, you will understand the device better. Will you be interested in learning more about the technical specs of the flow controllers, power flow controllers? If you're interested, raise your hand, please. All right, fantastic. How about the last one? You have a device there, but the SIM or the tools in the planning, SIM or Synergy, they don't have the capability or the modules for the device when you are doing the study or planning study. Will you be interested in the detailed modeling in SIM and the Synergy for the feasibility study of the power flow controller adoption? If you're interested, raise your hand. This one is a more technical. Sounds like you are really interested in trying to know more of the weeds part. And if you need to know more, Michael here, he can walk you through. All right, the next question. what are your concerns of power flow controller adoption? Indeed, I don't have option for you to select from. You need to tell me what is your concern. There is a device already on the market, and some utility already done the demonstration project in collaboration with the vendors and the consulting firms, from the feasibility study in the simulation to the field demonstration. It seems that there is showing the early sign of the potential for the more widespread the scale up deployment. What is the additional, or what is your concern for this technology adoption? Any volunteer want to share your view on this technology? If you can come to the mic, just share your thoughts or concerns. Darren, you have some words?
Only because nobody else is stepping up.
Oh,
So, no, I figured I'd break the ice. Really cool technology, really cool presentation. I guess the one thing that I would have in mind, obviously the benefit cost analysis, but in addition to that, maybe an aspect of that is putting additional devices out there on the field. Those are more devices that could be fail points. They do need to be maintained. They need standards to be able to reliably and dependably safely put them where they need to go. So just factoring all of that into consideration when figuring out what's going to make the best sense. Should we have something that actively manages power flow control, or should we use more traditional passive means of trying to keep things balanced and recognizing that there's going to be some degree of imbalance, right? So that's all. Thank you.
That's a great question. Yeah, we've heard kind of striking that balance before, and when trying to determine whether it's a good fit for certain conditions, that has often come up as a consideration. So I think that's a great one. I think that right now it's being utilized a lot, obviously in the pilot stages. There's been about a dozen pilots so far from different utilities, and people are really trying to get a feel for really how to use it. So they're getting more and more comfortable with what it does for the system. And it seems thus far in all the pilots to be pretty reliable as far as uptime and everything else. But obviously it isn't a piece of, technology that's been out there for 20 or 30 years that people can say, yeah, I'm confident that this is going to do this thing. So I think that the question is very valid. And I know one thing that the manufacturer points to as kind of somewhat of a benefit is because it is shunt connected, when it does fail, it kind of fails to what they call a normal operating condition. So yeah, you lose the benefit of the device, but it hasn't necessarily, like if a car runs into it, it's not an outage per se. You've just lost the benefit of what it was giving as, a device balancing the system.
So it's not do or die issue. It's just like if you see you have the improvement during the failure of the shunt devices there.
Mm-hmm.
John, do you have any words?
Just curious about protection. You've got reclosers, you've got all kinds of devices moving. We've seen the industry inundated with interactions between inverters. So you've got a distribution feeder with batteries, with solar. How is this going to respond to faults? And how is it going to respond to getting multiple reclosures back into the fault?
You know what, Jiang? Our DR working group meeting this afternoon, we have a DR stability risk analysis per session. It sounds like you are well positioned to attend that one. Indeed, Mike will share more lights. But how about that? Even before that, I will let Mike to give you some of the heads up. What will be potential issues for that topic? Is indeed a very interesting topic there.
Yeah, I'm glad you brought it up. That was the one that I had in mind, that if no one else offered anything up, I was going to mention this one in particular. So thus far, we haven't seen any real interaction with protective devices because of the time scale on which it operates. It tends to be closer to that like 10-second operating time span. So any kind of transient fault events have typically happened and they get cleared before this device can operate, but it operates on a time scale that is still faster than voltage regulators and the other equipment out there. So it kind of hits that sweet spot where it is going to follow the load really well and follow DER really well, like PV, but it's slow enough that it'll get out of the way of a lot of the protection schemes as far as the transient blips that come up. But there was a second part of your question too, I think. Oh, for reclosing shots. When it loses power, it is going to wait for a certain amount of time after, similar to like a DER device would, where it's going to wait for an adjustable amount of time. So if a utility wants it to come back on very quickly after an event and get back to work, it'll do that. But I think by default, it's programmed to wait for like 5 minutes of stable voltage, similar to what a PV might do, before it re-engages and starts balancing the circuit again.
Okay. So you said you estimated about 50,000 to install it. I assume it doesn't require breakers, MOVs. It's just you just connect it in with a jumper. It's done.
Essentially, yeah.
Okay.
You drop it on site. You have a riser going up the pole, and you just depending upon the control mode. I think right now all installations include it, but there are 2 CTs, kind of upstream and downstream, so you know what the neutral current is going through that way. And then it just pulls power down on all the phases, terminates in the device.
Okay. Thanks.
John, which utility to serve for your house?
I have a 22 kW generator and I'm not worried about any of this stuff.
Thanks. Any more concern?
Hi,
What?
Vlad Zayats. I'm at the Massachusetts Department of Public Utilities, Electric Power Division. Are my costs as working for the regulator is with costs? When we install this device, are the costs shared on that feeder to the customers connected to the feeder, or are you thinking of all the ratepayers responsible?
So that's a great question. I don't have the answer to it. I think it depends upon, I would assume, the utility that's kind of picking up. Right now, a lot of these pilots have been through, grant funded things. So I'm not sure that it has actually been worked into several rate cases, but I would say that I've been more focused on the power system sides of things, and I have not gotten into as much of the BCA and rate case side.
How expensive would it be to run a service area study, looking at all the feeders where these may be installed and the kinds of benefits that they could provide?
So they can go pretty quick now, and it depends upon the number of circuits that need to be put in. But if the number of sites is relatively small, like approximately where you want to put the device, and you're not throwing a really wide net at 1,000 circuits, studies can be done in a few days, essentially.
Thank you.
And if you build more automation, they're trying to automate all the Python script. You can even do it even faster, right? Just one click and you can automate all the results. It could be.
Yeah, it is very automatable.
Yes. Great. That's good news then. Michael, you will help with all the automation and then trying to if a utility is interested, he can automate all the procedure Python script and you can run a study for the screens for all the good location for your territory then.
We have done that for some of the screening already, yeah.
Oh, fantastic. That's good news.
Okay, yeah, I just wanted to share my thoughts, and I'm from the regulatory space as well. So, yeah, again, I'm with New Mexico Public Regulation Commission, but concerns on the flow controller adoption. I think for me, it really boils down to this may look like defer wires upgrades on paper in the near term, and I guess my concern is in alignment with that. Control complexity issues and you're looking at protection, coordination, uncertainty sometimes. So I think this gentleman's question was kind of an intersection of economics and maybe a sociological issue, but my answer to your question was really kind of who benefits from this, right? So that's an economics question, a sociology in some cases, but I'm electrical, but anyway, those are my thoughts, and thank you.
Yeah, those are great thoughts. And again, the only comment I can really make to that side of the house is I know part of many of the grants that have been proposed have been to have projects in kind of the disenfranchised type communities. So there has been efforts in order to try to benefit those areas a little bit more. But I would say I won't speak beyond my depth, and that's about the depth I can get into on that topic.
But yeah, you summarized basically what I was saying there too. I'm not an economist, so thank you.
All right, fantastic. Thanks so much. Oh, Obadiah, you want to have some words?
Yeah, just a question. Sorry, I'm not a power engineer, so
you know power and engineering enough.
I just talked to them. So, yeah, when we explored whether or not this technology would be helpful, our distribution planners felt that it wasn't really something that could save them money on the distribution system. And I'm curious sort of how applicable based on different system architectures and geographies you feel this is. Is this something we should be really excited about creating a lot of capacity within suburban systems or suburban and urban systems, or is this more applicable to rural areas or some of both? And I'll add one thing that on our system, it's sort of a looped system where we have a lot of ability to switch between feeders. And so I think reconfiguration is typically an option for us during planned maintenance if we see imbalance. But yeah, curious your thoughts about that and how broadly you looked at national grid system.
Sure. So that's a great question. Where to start? I would say that it is definitely system dependent. So we, even within, specific systems, we see some areas that are good fits and others that aren't. And it usually comes down to the amount of imbalance that's in the system. And then even if you have a lot of imbalance, if your systems are very short and you have relatively beefy conductor on the system, you're going to have imbalance on the system, but you're not going to have all of the manifestations of the power quality issues that come with the longer rural circuits. So definitely in rural applications, especially where you have those long single phase laterals that often wind out there, that's a very clear case for this device. We have seen more urban applications that did have imbalance want this device. The one challenge that I'd say in more of the urban applications is that it is a pad mounted device. So siting it can be a little bit more challenging in those areas as well. We've seen some utilities make it work where they're like, we want to try to put it out here, and they have found locations for it. So that's been great. But I would say that as you get more into urban systems, from my experience, oftentimes they're a little bit more balanced. They're built shorter, more robust, and you don't see as many application benefits as you do on some of the others that are a little bit more rural.
Yeah, thanks so much. All the great questions. Indeed, we have more discussions, but this discussion will cover both the flash interconnection and the power flow controllers. So the first discussion here, just trying to summarize it, and the flow controller is really just trying to balance the phase current and the thermal loading and the location and upstream of the flow controller. And then the beauty about the device is really trying to flatten the voltage profile and also the voltage profile there. They could increase the hosting capacity in the range of, I put a question mark. It really depends on your system, depends on your case. So that is, there's no clear, there's no definite answers, numbers I should put in. I just try to put some numbers for you to think about. And in general, this also depends on your planning criteria as well. As someone said, sometimes some utility, they only have the 10% to 15% imbalancing. Some utility probably even less. Some utility even more. So that depends on your case. The increase the DR hosting capacity is changing. So there's a lot of factors contribute to this. And the flow controller, as I talk about, there's no DER, no load curtailment, which is great news. Otherwise, the developer always concerned how much curtailment for my plant. If it's too much, and how can I have my finance with when I talk to the bank, right? So there's a lot of other issues. And in the upside, and for the flat interconnections, definitely will dynamically limit the DR output or load withdrawn, and potentially can really increase the hosting capacity to a few times, or depends on how much curtailment you can accept. As I talk about the example, Avangrid did a demonstration project. They increased the DR hosting capacity from 7.6 megawatt to 15 megawatt with modest curtailment there. That depends on how much curtailment you can accept that. And one of the caveat, as I will talk about, because you have the curtailment, particularly for the solar or DRs, the financially uncertainty for the DR developers, and how do you accommodate that? Maybe my first discussion point. They talk about, I think the speakers talk so well about what is currently has been done, has been pilot. If you look at this, the devices will be there for 20 years. The flat interconnection there will not be taken away in a few years, right? But in the next few years, when the device is in the field, your load has a load growth. If you do more electrification, for example, you have a load growth. The question here is that, what it would be the impact from your load growth on the performance of the technology here? For example, for the flow controllers, well, your load growth, for example, will that increase? By the way, for the system, so basically your load growth will increase the DR hosting capacity because in general, because your DR will serve the load, it will not really congested the grid asset. But then the next question here is, how about DR hosting capacity gain from the flow controllers? Well, that depends whether upon the system imbalance is improved or not from the load growth. Is that right?
Yeah, that's right. So that gets back to what we were talking about whether it's single phase or three phase, and then the types of voltage control that are also allowed.
Right.
So if voltage control is not allowed at all, you're going to pull your phases together, which can open up a little bit of bandwidth. But
Right.
it can also optimize the voltage control of the DER itself, so you can get a little bit more benefit out of it from that perspective as well, kind of in that unconstrained region in the operating paper plus the voltage controlled region.
Yeah, fantastic. That basically means that the load growth indeed will increase the DR hosting capacity, depends upon the performance of flow controllers, really depends on if your system imbalance will be getting worse or is getting improved. Then the same question here, if you have the load growth in the next few years, you deploy the flash interconnection, and then, well, the load growth, will that reduce the DR curtailment with load growth? Is that the right statement, or is that your?
Yeah, first I have to say I feel like I'm in a high school debate here, like Leo going back and forth, and like,
I'm not in the middle.
Right. So the premise of that question, it's correct, but there's also the time variable.
Yes.
So your new load profile may not perfectly match your generation profile, and you still, so it's not a total 1-for-1. You add more load, and then, therefore, so it really does come down to like when, what does that new load profiles look like? But yes, I mean, obviously the more load coming on, hopefully that would decrease the amount of curtailment on like a DER generation device. And then inversely, as you're bringing on, more, or what was the second part? So increased load curtailment with increased load growth. Yeah, that probably is accurate too, with that caveat of what type of load and what does the load profile look like over a period of time.
Yeah, so that depends on the load shape. Correct. If your load shape it's a friendly load shape, and then you will increase the hosting capacity, reduce the curtailment. But your load shape is not a greater friendly load shape, and then you're in a little bit of trouble. So this is just trying to provide us some, forward looking, if you deploy the technology now based on the study like the gentleman did, based on current grid condition, with the grid transition, with more load integrated to the grid, how this device or how this technology will be performing. The good thing here is with the load growth, the DR hosting capacity will be increased in general. The DR curtailment positive side will be reduced, but maybe that has no impact, depends on the load growth, load profile. This is one second. How about the behind meter solar growth? How will that impact the both technology here then? I will let Mike to start with the flow controller and just say.
So I don't know that behind the meter solar growth is really going to have too much impact on the flow controller operation, besides the fact that it will be able to smooth out any imbalance that's introduced, which is what those case studies were that we looked at earlier about EV adoption and PV adoption. That assumed residential behind the meter growth, and we assumed that it would exacerbate the system kind of under a worst case condition, and it was able to smooth out the increased imbalance and kind of help those.
All right, fantastic. The question here is whether your behind the meter solar growth will make the imbalance worse or is improve, right? How about that? For the flash interconnection, when you see if you now the Excel Energy adopt the flash interconnection with the controller all set up, tomorrow we have the behind the meter solar growth for that feeder circuit. How will that impact my the flash interconnection and my DR hosting capacity and curtailment?
Yeah, I mean, potentially as you bring more behind the meter PV, that would coincide with, additional curtailment. Hopefully your planning process kind of takes this into account and is looking at further out as far as what is the growth, is there going to be additional incentives that would, have a larger growth? Is that growth of behind the meter PV pretty steady? I think more and more that's become better forecasted. So hopefully you're basically taking that growth into your forecasting models. But yes, absolutely. If all of a sudden there's a large influx of behind the meter solar in aggregate, that is going to, directly coincide with your larger PV that is looking at flexible interconnection.
That's fantastic. Basically, when you are deploying the technology, you not only look at the current grid condition, you also need to be a little bit forward looking. What will in the next few years, what will come into the picture? How that will impact or benefit even sometimes the performance of the technologies here.
One thing I'll ask, because I actually didn't make obviously when we're talking about flexible interconnections, we were definitely doing it in the case of like a single site, a single point. But broadly, if you say flexible interconnection in the industry, you do start to hear more like aggregation of,
right,
virtual power plants. Is that flexible interconnection? And so you do have to, it's kind of like the world of DERMS. When you say DERMS, there's not just one perfect definition. So you do have to kind of drill down what the context of like flexible interconnection is.
Fantastic. Regarding the flat interconnection, just trying to pull a little bit more figures here. So ESIG did a webinar in October 2025, and Avangrid came in to share their field demonstration project for the flat interconnection lesson learned from there. So this is the one chart here. Indeed, you can see that the Avangrid basically categorize the curtailment cluster in a different category here, and then there are additional curtailment in the field operation, basically due to the fail-safe mode. When you lose the communication, they see some of the curtailment there. So this is just bring up another additional topic here. When we do the planning study may not well capture all the operational conditions in there. So ESIG in the afternoon, the first section will be the planning operation in grid, sorry, it's operational, is operation incorporation in the planning. There is a joint section in the working group in the, today at 1 o'clock we're here. So just want to let you know, this is just one example from the Mark, from the Jiang. They did a study with the extra energy, the planning to estimate the curtailment. But from the grid operation perspective, you have more grid conditions that has not been captured by the planning study. For example, the real-time grid controller, some utility deploy that every few seconds, every minute, for example, but Mark, the study is every hour. So basically, how did you incorporate the operational consideration into the planning? That's a hot topic as well. Hopefully ESIG will shed more light on that in the afternoon section. The second one here is, like John talked about this. How did you set up the controller configuration? And indeed, this is based on the Avangrid, the webinar there. Indeed, usually this is the most likely the developers will not know all the details. And the utility will set up the configuration for the controllers. They're using, they usually based on the thermal rating of the constrained equipment. For example, I know the National Grid in New York, they said, hey, I only consider the distribution substation with the transformers. I'm not considering any of the feeder level constraints at all. But Avangrid said I will consider both, the transformers and the feeder circuit conductors as well. And they are based on the static thermal limit of the asset. The question here to you here is, what a dynamic asset rating will be able to help? For example, in the transformers, utility will use the summer rating and the winter rating. But when they do the flash interconnection, they may only use the summer rating, which is lower, means you will have more curtailment. So there is a lot of other factors you need to consider for the flash interconnection. It's not only just about, hey, this is a technology, and how did you set up the controllers? How did you factor in? How did you make the decision there? I think in my opinion, we all need to work together. What's the best practice to benefit the utility, benefit the customers, benefit the developers? And the key takeaway here is, this is maybe my personal opinion, as the flow control could be low cost, effective way to increase the DR hosting capacity and the load hosting capacity, and then improve the grid efficiency when the desired gain of the hosting capacity is modest. So basically you can increase, but not all the grid conditions is a good candidate for this technology. And the second one for the flash interconnection is also a very effective hosting capacity solutions here, but you really need to be careful about what is your potential curtailment. And then the developer always, number one concern they have is how much you want to curtail me if I participate in your program, right? So that's, we still have a lot of work to do, and we are on the trajectory to get more done. So that way our community will be more familiar with all the technologies here. As I said, this is what we are covered in this tutorial. And in the today's in the afternoon, we have the working group meetings. We will shed more lights on how did you incorporate the operational conditions into the planning. We will also talk about long-term capacity solution that could include the proactive planning framework or integrated planning. So that will be in the working group, but also for the panels in the next 2 or 3 days. I think that concludes our tutorial here. But I have just a minor thing, just talk about the schedule. So we will have the lunch just outside of this room from noon to 1 o'clock. Now we will have the joint working group session to talk about operational incorporation, interplanning. The locations here starting at 1. Is that right, Ryan? 1 o'clock. And after that, the second half, so it's starting at 3:30, and we will have 2 working group meetings. One is the DER working group meeting, started at 3:30. The location is not here. The DER working group meeting, it will be the main hotel, Salon C. That will be the room. And there will be some signals there to where to go. But if you don't know, if you are interested in the DR working group work, you don't know where to go, feel free to get a hold of any of the ESIG staff. Even the registration, we will be able to guide you to where to go. Of course, you can find me there or over there. The second working group meeting is joint working group meeting is the ESIG planning and operation working group meeting. That location will be here at 3:30. So that's basically the agenda for today's afternoon. They will have working group meetings, and you are very, very encouraged to participate and share your experience and the concerns. With that, and we'll conclude this tutorial.